بسم الله الرحمن الرحيم. الحمد لله
والصلاة والسلام على رسول الله.
السلام عليكم ورحمة الله وبركاته. سعادة
المهندس محمد عبد الله، زعيم الأمين العام للاتحاد العربي للأسمدة، الأخوة المشاركين من الدول الأعضاء في الاتحاد، الزملاء من أوميفكو، الأخوة والأخوات الحاضرين، نرحب بكم في سلطنة عمان في هذه الأيام المباركة، أيام نحتفل فيها بالعيد الوطني 48، ونسأل الله سبحانه وتعالى أن يعم الأمن والأمان على جميع العالم. نرحب بكم في هذه الورشة، ورشة التشغيل والصيانة في مجال صناعة الأسمدة، التي ينظمها الاتحاد العربي للأسمدة ضمن فعاليات اللجنة الفنية، والتي تهدف إلى الارتقاء بأداء المؤسسات والمصانع في مجال التشغيل والصيانة حتى نحقق أهداف هذا الاستثمار: توفير الغذاء للعالم، وأيضا استخدام أحدث التكنولوجيا بأقل أضرار على البيئة. لا أريد أن أطيل عليكم، سأترك المجال للمتحدثين في الإسهاب في هذه الأمور وكيفية الامتياز في التشغيل. دقيقة سلامة نطلبها من هوتيل HSC مانيجر، بيعطينا البريفنج اندكشن في حالة أن لو لا قدر الله حصل أي ظرف طارئ. فلور is yours, Mr. Jacob.
Good morning, ladies and gentlemen. First of all, we welcome you all to the Grand Lady Mosque. Thank you for the, I think it's the first time you all here. And my name is Suraj Ravindra. I won't take much of your time. Just I would like to brief you on the safety procedures of the hotel. Our hotel is fully protected with all the fire detection and protection systems as per the local legal requirements as well as the international standards. We have all the fire fighting equipments at all operational locations of the hotel. So also we have an emergency response team in case there's a fire. They will do investigation. And we have an addressable fire alarm system which is connected to our building. So as you all know, if there's a fire in the building, it comes with an alarm along with the evacuation message. So for that you need to know the nearest fire exit. So from this ballroom, the nearest fire exit, you can see fire exit door is there, left to your seat. Or also you can use, but this is the nearest one. So if you go to use that door, take left from there, go straight through the corridor, it will take you to outside of the building. The fire assembly point is at the corner of the facing the room. Anyway, no issues. As of today, we have not planned any mock drills or something, so that if there is any evacuation message, definitely you need to evacuate the building using the nearest fire. Also, our team will be there to guide you, so you don't have to panic. So, any questions? Regarding the restrooms, we have two restrooms. The two.
مشكلة هذا.
One at the
كفي هذا أي.
entrance from the blue side, one at the entrance from the grand wall side. So if somebody wants to pray, they can use the restrooms over there where we have prayer. If you have any questions,
أحسن من هذا؟ أحسن من ذاك؟
thank you so much. I wish you all the
استعمل ذاك يعني. إن شاء الله.
السلام عليكم ورحمة الله وبركاته. الحمد لله الذي خلق فسوى، والذي قدر فهدى، الذي أخرج المرعى، والصلاة والسلام على سيدنا محمد الذي اصطفى. أيها الأحبة، السلام عليكم ورحمة الله وبركاته ثانية، وأهلا ومرحبا بكم هنا في مسقط في سلطنة عمان، في أرض العروبة والإسلام، في هذا البلد المبارك الذي نحتفل هذه الأيام بعيده الوطني، وندعو الله سبحانه وتعالى أن يحفظ هذا البلد وأهله وهذه السلطنة بكل خير، وكل عام وهم بأسعد حال وفي أمان وسلام إن شاء الله. الشكر والجزيل لشركة أومفكو على استضافتها هذه الورشة المباركة، والشكر موصول للأخ محمد المسؤولي على افتتاح هذه الورشة. كما تقدم لحضراتكم باسمي ونيابة عن رئيس مجلس إدارة الاتحاد الأخ المهندس عوض الصابر، ونيابة عن ممثل سلطنة عمان الأخ الفاضل أحمد المغروبي، والأخوة في مجلس الإدارة، أبعث لكم تحياتهم وتمنياتهم بنجاح هذه الورشة المباركة. الشكر الجزيل لفريق العمل الذي ساهم في جعل هذه الورشة بشكلها الحالي، ونشكر لهم حسن الاستقبال للضيوف وكرم الضيافة والعناية الرائعة لتجعل كل منا سعيد في هذا البلد المحفوظ بإذن الله. أيها الأحبة، كما لا يفوتني أن أتقدم بالشكر الجزيل إلى شركتي ستامي كاربون وديسن على قيامهم بتقديم النصح والإرشاد والمحاضرات القيمة في مجال الصيانة والتشغيل لمعامل الأسمدة. دعوني أن أتكلم باللغة العربية، وهذا ما أحدده. السؤال ماذا أقول؟ لا تلمني في هواها، أنا لا أهوى سواها، لغة الضاد هذه، لغة الضاد هذه رفع الله لوجهه. نحن هنا في هذا الاجتماع المبارك جئنا من المغرب العربي إلى الخليج العربي، من مصر، من الأردن، من كافة الدول العربية، نلتقي هنا أولا لإحياء الشعور القومي فيما بيننا، وإحياء التواصل التاريخي وتواصل الدم بين هذه الشعوب العربية، الشعب العربي آسفا، لبناء علاقة صناعية ناجحة. وهذه مهمة الاتحاد العربي للأسمدة. مهمة الاتحاد العربي للأسمدة، هذه المنظمة الغير ربحية، هي منصة للإيصال والتواصل بين صناع الأسمدة في الوطن العربي. هنا ليس فقط أن نسمع المحاضرات، نعم جزء من هذه الورشة، لكن هنا نبدي معاناتنا ومشاكلنا وتحدياتنا التي نجدها في مصانعنا جميعا. كل لديه كثير من المشاكل والتحديات، لكنها ليست في كل المصانع تساوي، ولهذا ما موجود في شركة أومفكو قد لا يكون موجود في لافيكو في ليبيا أو في الإسكندرية. هناك اختلاف في نوع المشكلة، وأيضا لعصف الأذهان بالمشاكل التي سنواجهها مستقبلا في صناعتنا، سواء على مستوى الصيانة أو على مستوى التشغيل. ولهذا هناك ضرورة حقيقة أن نتوسع بشكل آخر. عدم أنا أجد قد وجد كل منكم صاحبه فجلس بجنبه. أنا أرى أن نختلط اختلاطا آخر بحيث نكون نتعارف على بعضنا بشكل أوسع، ونجلس على طاولة واحدة من مصانع مختلفة ونتعرف على مشاكل الآخرين، وأيضا لتوثيق العلاقات بيننا إن شاء الله تعالى. أيها الأحبة، لا أحب أن أطيل عليكم لأننا لدينا كثير من المحاضرات. هذا هذه المحاضرات مهمة، لكن أقول مرة ثانية أن هناك أهمية أخرى. هذا عدد كبير من عدد النواب من الحضور يستطيعون أن ينقلون هذه الرسالة وما يجدوه في هذه الورشة إلى مصانع. لا يكتفي بأن يكون هو يأخذ المعلومة وحده. لذلك الاهتمام بما يوجد في الورشة ومحاولة أن يلقي البرزنتيشن أو المحاضرة في شركته، ونحن كاتحاد عربي للأسمدة ستكون لدينا المحاضرات مسجلة كاملة على الموقع، بإمكان أي منكم أن يقوم بأخذ هذه المعلومات وتحويلها إلى محاضرة علمية حتى يستفيد بقية زملائه في شركته. أنت في قسم الصيانة، لديك في قسم الصيانة الميكانيكية أو الكهربائية أو الأجهزة عدد كبير منهم، تعد لهم محاضرة تصل بهذا العملية. تكون الورشة بدلا فيها 65 سيكون هناك مئات قد سمع واستفاد من هذه الورشة، وهذه هي المهمة لهم. الذي نراه في ورشتنا هذه أن ننقل قصص النجاح والتجارب الناجحة في شركاتنا لكي يستفيد منها الآخرين، ونذكر المشاكل التي واجهتنا في تشغيلنا سواء في فترة الكوميشننج التاسع أو في فترة التشغيل التجاري. ننقلها ونسميها الجود براكتس وقصص النجاح. هذه أيضا مهمة لعصف الأذهان وتبادل الخبرات بيننا ولعمل نتورك ناجح إن شاء الله تعالى. بارك الله فيكم وجزاكم الله خيرا. كرروا شكري الجزيل لحضراتكم ولشركة أوموفكور لحسن الاستقبال وكرم الضيافة، ولكم جميعا أيها الأخوة الشكر والتقدير، متمنيا لكم قضاء وقتا ممتعا إن شاء الله في هذا البلد العامر. والسلام عليكم ورحمة الله وبركاته.
Workshop program by inviting Dr. Tarek Al-Hawari from the City Group to present on data assessment and revamped option for ammonia and urea.
Assalamu alaikum. So, good morning everybody. I would like to thank OMIFCO and the AFA for hosting this event. Very happy to be here. I have two presentations.
So I would like to start. I would start with my first presentation, which is about digitalization. The reason why I'm presenting digitalization because it's becoming a bigger part of our lives every day. Yeah? You see it in your normal behavior when you do shopping. When you go to Joomla or to souk.com and you buy something, and the next time you go to Facebook, you see an advertisement from the same product you bought. Yeah, this is how they're handling the data today. Yeah? And the same is done in our industry, but it's just in the beginning. Yeah? So if you look, for example, on turbine, on airplanes, yeah, all of these turbines, which keep the airplane safe, are monitored by Rolls-Royce in England. Yeah? They know everything about all the turbines at every time. Yeah? The data is transmitted, so they know when they do maintenance and all of this. This can be also applied for fertilizer plants and in the plant as a total. And I would like to show you some examples we have done in the past to optimize the uptime and the efficiency of these plants. Yeah? To give you some use cases and some ideas about digital twins and all of this. So my name is Tarek Al-Hawari. I'm working for ThyssenKrupp Industrial Solutions, formerly known, we were part of UDE, maybe you know us, yeah? And we have a long history in the fertilizer business. But I would like to show you about our company. It is one of the oldest companies in Germany. It employs more than 150,000 employees worldwide. We have 200 years experience. Yeah, it is originally a steel company, and then over the years everything was combined: elevators, fertilizer, chemicals. A huge number of machines and systems implemented worldwide, chemical installations over 2,500, and still, alhamdulillah, we are still more than 70% technical people. Yeah, so the engineer still means something in our company. It's not all managers, it's still technical and engineers, so innovation is still an innovation-driven company. Coming to our business area, industrial solutions, as you can see, it's also widespread. Yeah, we do electrolyzers and polymer technologies. Fertilizer is very important, yeah, for us. Nitric acid, DAP, MIP, ammonia, urea, everything is available. Methanol also. Industrial specialties like coke technologies we have in our portfolio. Cement, it's one of the major milestones. Of course, also mining, the big excavators. We have a big field of service, which part of the presentation is today, and system engineering. Yeah. When we speak about digitalization, if you want to speak about digitalization, you need to have a basis when you talk about this. Yeah. So we have a lot of installed units where we are cooperating with and getting the data from them and analyzing this data offline or online, depends on the client. And from this, we were able to develop a strategy how digitalization can become part of the daily operation and maintenance life. Yeah. So if you look on what digitalization means, digitalization can work as a catalyst. It works as a catalyst in form of uptime and efficiency. As you can see here, it is a little bit weak, but it means status quo. It's light gray. And if you put digitalization above, you analyze the data which is already available in your plant. If you look on an ammonia and urea plant, including utilities, how much instrument tags do you have? Between 6,000 and 10,000. All the data included. And if you analyze this data without adding anything to it, you will have enough data to analyze the plant, to see what the plant is doing, that you can predict what will happen in the plant. Of course, if a scaffolder hits the emergency shut-off button for compressor, of course you can do nothing against it, yeah? Like it happens in the commissioning many times. But in normal operation, you can predict. You can see if bearing temperatures are changing, if they're changing unsystematically, yeah? They're going up and down over weeks. You can see that there's a tendency that the compressor might fail. What this is offering is, if you add this digitalization, it will increase your uptime and your efficiency. It will allow you to make quick decisions and improve your planning. Analyzing data from a plant by a technology provider like us, together with the clients, with the plant operators, it's not like that we are interacting with you in the plant itself. We will never act from Germany to your DCS. You have to consider this as an additional pair of eyes, which gives a recommendation as an assistant. Yeah, this is the idea behind of it. We read the data, we analyze it, we give you recommendations in form of reporting, or even that field personnel will be at your site. This is the idea behind of it. So, what is our USP? We have a broad experience in all of this. We have a domain expertise, we have capabilities. We have a deep knowledge. So this means we have a domain expertise in terms of design, also of operation of plants, and in digitalization. ThyssenKrupp is a big company that we are hosting also IT specialists, mathematicians who are specialized in statistics. They don't know nothing about ammonia and urea plants or nitrate plants. But if you give them the data, they see a behavior, they see a pattern, and then they come back to us, to process engineers, and ask us, okay, this is abnormal. Do you have an explanation for this? So the mathematicians and the IT specialists are coordinating together with the process engineers to find the best solution for the clients. We worked many projects with our clients deeply together, so we know what the client wants. Yeah, but for sure the main topic is always keep the plant online, which is even more important than to keep it efficient. And then the second point is keep it efficient. Efficient in terms of reduce natural gas, coal or naphtha, and what becomes more and more important, save water. Now, nowadays, water is also a critical parameter in the efficiency of ammonia plants or urea plants or whatever. Yeah? That we can cover the entire process technically in terms of process, mathematicians, and IT, and considered as a triangle, the knowledge we are getting from the data of the plants is going backwards to the plant operators, to the plant owners. So it's a triangle. It's a triangle between the plant operators, the process, and the digitalization team. Yeah. So the knowledge which is created by doing the statistical analysis is going backwards to the clients, who more and more become specialized in these fields. Yeah. Because if you look on the ammonia and urea industry, for example, this is where I'm from, it's a conservative industry. I can say it like this, yeah. If you go to a client and I ask him, I want online data from you to analyze it directly and say, I can show you something, some hidden risks and all of this, they say, okay, we find them ourselves. But I can assure you, for many use cases, it is impossible for an operation and maintenance team to look at the whole plant all the time completely. It's not possible. No human can do this, yeah? Independent of how big the shifts are. But computer systems can do this. They can observe the whole system, they can analyze it, they can find abnormal patterns, and they can highlight them for you. So how is this working? Here we have a nice picture of a reforming section, primary and secondary reformer. It contains a lot of instruments in terms of pressure drop, flow indicators, and temperatures. So this data is transferred, let's say, into a cloud system. Yeah, it can be done offline or online, whatever you prefer, but it is extracted from the DCS system, most probably from the historian. Here, of course, the basis is the finer the data is, the better they are. Yeah, if you give me, for example, if you analyze the data and you have 1 hour average, and you're talking about the vibration of a compressor, which comes every millisecond or every second, then the data is useless. The data needs to be in a time frame which can be used. Yeah? So this means online data transfer, which can be done every second, is more preferred than getting offline data from a historian, from the DCS historian. Yeah? Then this data is analyzed by human interface or by the artificial intelligence. It becomes visible in a computing surface, which allows you to calculate KPIs, make graphical analysis, and at the end, the results are filed in a report, or as I said, to field services, directly to our clients. This is the way the chain works. So then we have, the most important thing is, as I said before, the data analytics and the machine learning are done independent from any process knowledge. I will come later to a point, there's a difference between the approaches. Yeah? The data analytics itself is done on machine basis. And it can be done also independent from plants. When I started this initiative, for example, I started in Egypt. Because Ude, or formerly known as Ude, we have 9 similar plants in Egypt, where even the instrumentation has the same number in Egypt. So this means if you develop this system for one plant in Egypt, you can apply it for all of them. This is a special case in Egypt. But the data we have put behind it is metadata. This means I'm not putting instrument tag 03001 as reformer outlet temperature. No, it is called the reformer outlet temperature, which is adapted for each plant itself. This means I can easily compare plants with each other and create a benchmark. Of course, anonymous, yeah, because every data owner keeps its data. Yeah, none of the data will become ever public. Yeah, the data is just stored in the cloud, and the benchmark is done on an anonymous basis. But you can see then how the plant is performing compared to other plants. Yeah, you can even see how the plant is performing between different shifts, if you want, if the plant manager is interested in this, because we see, and it's obvious, that there are performance differences between day and night shift. I know it. I worked also night shift before. Yeah, so for sure. Yeah. And this analytic is combined with the domain expertise, which are simply post engineers who are doing nothing then analyzing data all day. in our company. They're getting the results from the mathematicians. They see, okay, here we have differences, we have abnormal behavior in means of standard deviation, for example, and they're looking behind in the trip schedules, PIDs, and all of this, and comparing it. And this does not mean that it's also limited to the DCS system alone. You cannot access an ESD system because it's legally not correct to do it. But you can access a Bentley Nevada, for example, for machines, for compressors, system 1, whatever your ITCC systems. This is easy to access also, yeah? So there are 3 approaches to do this, and the best solution for all of this is to combine them, yeah? The first one is to do it data-driven. This means you do it generically. You see the data as a total, not differentiating between ammonia or urea or nitrates. Use machine learning methods like neural networks, and you let the experts analyze the results and see, just in terms of numbers, what are the differences. The next one is expert-driven. If you go and see you have some knowledge about specifications and general operation patterns without knowing the physics behind it. Just from the operation point of view, you know the delta P across a turbine stages or a compressor stages is changing. What's the reason behind of this? Every operator knows this. Yeah, he doesn't need to know the thermodynamics behind of this, just from experience. So it's experience-driven data. And the final one is, if you put an ESP model behind it, or HYSYS, or Pro2, or whatever you prefer, and you integrate the operation data into a simulation. When we design a plant, we set up an ESP model, for example, and we define the data. Yeah? And based on this data, the plant will be built. When we analyze the data, for example, you want to make a revamp. We got data from the plant based on the DCS screens, and then we fit this data into the simulation. Then in the next step is, how can the simulation be fitted to this operation data? And from this you can derive, for example, how the catalyst is aging, how the machine is performing. Do you have fouling on the heat exchangers? All of this can be derived from the operation data which is put into the simulation model. And at the end, all of these 3 approaches need to be combined to cover the whole plant process. Yeah, because there are some parts of the plant which cannot be easily covered by a simulation. Yeah? For example, this is pretty difficult to simulate a simple turbine in terms of efficiency in a simulator, yeah, because you don't have all the measurements. For example, a compressor is easy, a turbine not. Yeah? So the approaches which I said before, they are called black box and white box modeling. Yeah. So as I said before, the data needs to be defined. At the beginning, I would say the DCS data is more than enough. The instrument tags. Yeah. The data is transmitted. It will be analyzed, and the analyzation will become based on pure mathematical data. I will come later to this, or on a simulation data. Or the most preferred way is if you combine both. Yeah? This means, for example, if you look at an ammonia plant, you can simulate, for example, the reforming section of an ammonia plant is very easy to simulate. Yeah, because it's straightforward. If you come to an ammonia synthesis loop, it becomes complicated, yeah, because you have in the loop, you have the gas, which is the product which is taken away, the gas is circulating, and you have the syngas gas compressor behavior. This is a very complicated issue to analyze. And if you want to make a revamp, for example, the most complicated question in every revamp is always the behavior of the syn loop and then the syngas compressor. Because you have the compressor curve, and you have the curve in the syn loop about the pressure drop and the pressure behavior, which depending on the ammonia production. So these 2 need to come together to see how the syngas compressor will behave in the future, for example. This cannot be easily calculated in a simulation. This needs to be done based on operational data and mathematical approaches. So the idea behind of this would be, for example, you calculate, let's say, the ammonia plant in Espen, but the part of the syn loop and the compressor will be done mathematically, and you fit this model into the Espen simulation. And by this way, it is easily possible to get behind the problem. Yeah? This is the idea behind all of this. Yeah? This slide, I put it in the presentation because of one reason. If your plant is tripping, you don't need me or you don't need ThyssenKrupp, because in 99% of the cases, you know within minutes why the plant has tripped. You look in the ESD, you look in the first out, and now the plant has tripped because of this and this and this. It's easy. Yeah? But to see why something has happened or why something might happen in the future, to get a prediction, what might be the hidden risks, what is the danger for your plant, what is holding the plant back in terms of efficiency, this can be easily derived from data analysis over a certain amount of time. Yeah, because patterns are derived which are even not straightforward. Yeah? As I said before, for example, I have seen it that you have a bearing temperature for a syngas compressor, for example, yeah? Thrust bearing temperature, which was going like this. But if you look at over weeks, it was increasing. But nobody recognized it because the shifts were changing, and one day was up, one day was down. Then they went for vacation, then they came back, the next shift came, so the pattern was forgotten. And then one day, out of nothing, the temperature was so high they had to trip the compressor because they were afraid to damage the machine itself. So this would have been a good way to act in advance. Yeah, prescriptive. What can be done to prevent this will happen at the end? Yeah. So they could have, for example, at the end they found that there was a delta P across the stages which was too high, and they found that the valve behavior of one valve was incorrect. Yeah, the valve was wrongly tuned and it was damaged. Yeah, for example, this led to the fact that the delta P across the stage was too high and the shaft was moving. This is one example. Yeah. And the other things are which might happen also are, for example, that you have a wrong distribution in the firing in the primary reformer. Yeah, the heat patterns of the primary reformer, you can see it from the different header temperatures. Yeah, also they are changing differently because the tail gas is changing. All of this can be seen if you analyze the plant as a total continuously. Yeah, and you let the computer see the patterns and just show you the highlights. Yeah, and it keeps you away to look on it all of the time. So how is this done? If you talk about online data, this, for example, you have the machine. It's transferred by a data logging system. I will come to this on the next slide. It's recording the data from the DCS. The system, of course, itself is cyber secure. Yeah, because nobody would take the risk that the plant gets attacked by cybersecurity. So the plant will be connected, one directional. So the device is just reading from the DCS system. The device will transfer the data into a cloud system where everybody has access. This means ThyssenKrupp and the specific client will have access to this. The data will be visualized. It will be analyzed. KPIs will be derived, yeah, in terms of efficiency, fouling factors, catalyst activity, machine performance. And at the end, a report will be filed, also live services, and a direct link to a spare part library is generated, where it is also possible to get spare parts which are not available on the normal market anymore, yeah? Because the usual vendors, they got bankrupt, the companies have vanished. But we are still in ThyssenKrupp because we have a large network of spare parts. We were able to organize these spare parts. At the end, the system goes backwards to service engineers and technicians. The results will be analyzed. They go back to the client, and the client will implement them, yeah, to prevent that any danger will happen to this machine. This is the life cycle of the product. So how is this done? This here, I don't know if you can see it, is the surface in our Indigo cloud. You can see here very nicely the plants. So this means if you, for example, you put one of the plants in Egypt, then you can see here in Egypt, okay, the plant will be here. This is my plant. Yeah, you can access it. You can see all the data graphically or you can do it by KPIs, since you can see the main results. It's like a DCS analysis, but more specified on your needs. Yeah, and it shows you what are the abnormal patterns. What was the reason for the last behavior like this? What might be the next problem upcoming? It can be specified to the individual requirements of the clients. It's not a problem. The device which we propose to implement is this local analyze interface. This device is, let's say, half of the PlayStation, which you know from the kids. Yeah, it's that big. It's just a simple Pi computer which connects to the DCS. It records the data and transmits them. Yeah, this device was tested by the Technical Service Authority in Germany, the so-called TÜV, and they tried to hack it. Yeah, many times, and they were not able to do it. Yeah, so we got a certificate for cybersecurity. But in any case, it's always recommended that each DCS system itself also needs to be have a cybersecurity layer. Yeah, because what's the reason why DCS system got infiltrated today? Not because they're online, because somebody puts a USB stick inside which is dirty. Yeah, this is what 99% of the cases happens why DCS system got infiltrated. Yeah, we see it many times. You want to collect from some trend data there, you put a USB device inside, and then you have a problem. Yeah. So, and by this device, the data can be extracted, and then it can be taken into the cloud system, which also the client has access to. Yeah. The other solution would be that you have a DCS system of your plant, and you have an ERP system in your company for your office network. Yeah. For example, I have seen it in Saudi Arabia. There are companies, they have a DCS system and a PCS system, a process control system, where the process engineers have access to the DCS data. The screens are pretty similar, but they cannot access the plant itself. They can just read. So the easiest way for us would be to extract the data from the PCS, because me, as a process engineer, I don't want to interact with the DCS system at all. For me, it would be easier to go to an ERP or PCS system and get the data from there. Or if the data is stored on the cloud, on the servers of the client, we can access these servers. It's more easy. Yeah. But the basic solution would be to connect this device to the DCS system, and you will not access the DCS system itself. This device is using a so-called OPC client. It's an open protocol system, and you just extract the data from the end of the DCS, so it will not act with the controllers of the DCS. We will not tune the DCS or whatever. Yeah? It's just reading the data from the OPC connection. This is an example of what I can show you to maximize your life profits. Yeah? And I will adapt it later to ammonia and urea plants. This, maybe you know it, it's a PDH plant in Egypt, in Port Said. It was built by ThyssenKrupp. And you have external influences. Yeah? You have price in their base material, you have legal constraints. Yeah? In Egypt, for example, they have a very strict environmental law, law number 4. It is very strict in Egypt. The gas prices are changing, water prices are changing, so the plant needs to be optimized permanently. Yeah? And one way to do it is building a digital twin. This means you take a part of the plant and you mirror it by a simulation which you are fitting operational data into it. Yeah? For example, here. There you have for example, you have the dynamic external influences here upstream of the compressor. So the compressor is turbine driven. So how can the steam consumption be optimized? Because the gas separation later is done in this big column here, yeah? This C3 splitter. So we have the simulation. Here's the fracturing unit, which is this one. And we have put an SP model behind it, which is fitted by operational data. The data is coming continuously as swarms, and they are implemented and fitted into the simulation itself. And the simulation adapts its parameters to mirror the real plant and then it makes recommendations how the operation conditions can be changed to minimize, for example, the steam conditions and to still achieve the product capacity and the product quality. Yeah? Here you can see, for example, the turbine efficiency, how it is done. And you can see that the potential operating profit, which can be calculated, is compared to the current operating profit. Yeah? It's, for example, that you calculate the consumption figure of the plant life permanently. Yeah? This is one solution which can be done. We have other use cases. I will go on the first and last one. I will go shortly, and I will focus a little bit more. We did it in electrolysis plant, in ammonia plants and polymer plants. And electrolysis is pretty easy. Yeah? It is a very simple system. You put power, you put sodium chloride and water, and it separates it to sodium hydroxide, hydrogen, and chlorine. The good thing about electrolysis plants is, and this is unfortunately not in ammonia plant the case, it is a serial configuration. You have many electrolysis units with different electrolyzers connected in serial configuration. So, the main characteristic of such a plant is the voltage, and how the voltage, the transfer, is changing across the time, and from this you can see the degradation. And this you have many, many times, because it's a serial. You have several hundreds, and all of them pattern like this. So, you put the domain expertise, which is the chemical engineer. He sees, we have a coating degradation here, and when it reaches to this point, the electrode needs to be replaced. So, they preprocessed the data, they trended it, they classified the electrodes, and from this one they derived an experience model when the electrodes needs to be replaced in advance to prevent that the electrodes fails and stops the plant. So, this is the pattern they derived from it. They see, the degradation starts here. Here it's the renewable, and here it needs to be renewed latest because it becomes worse, worse, and worse. If you apply this pattern, what you learned, on your plant, then you have this one. Then you can see suddenly, I have a lot of them which needs to be replaced in the near future. I cannot wait until the next turnaround. I know this is not an ammonia plant. It's just an example how the system works. In an ammonia plant, the situation is a little complicated, or it's more complicated, because the plant is pretty big and the influences are widely spread. And for urea plants, it's the same. Urea plant is even more complicated because there, and this I will show in the last example, the product quality of the urea cannot be measured online, or it is hardly measured online. Mostly it's from lab analysis, so it's becoming it's offline data. In ammonia, you have directly the quality online. So to optimize the product quality of a urea plant, it's a little bit more complicated and needs a different approach. But I will show you this in the next example. So this means we're collecting all the data of the ammonia plant continuously, and we detect relationships. A variate analysis means, for example, the nitrogen content in the ammonia synthesis loop. It is a very important figure because it determines how the catalyst is performing. The ratio between hydrogen and nitrogen is an indicator how the kinetics are performing in the synthesis loop. So, variant analysis means if you put the parameter nitrogen content in the synthesis loop as your main parameter, then a variant analysis shows you what is influencing in the whole plant the nitrogen content in the loop. This can be, for example, the speed of the process compressor, the amount of steam of the process compressor turbine, for example, the amount of nitrogen in the natural gas. All of these parameters are influencing the nitrogen content in the synthesis loop. Most of them are known, but some of them are unknown, for example. Assuming, for example, you have a balanced plant. This means you're taking the syngas downstream to CO2 removal backwards to the reformer fuel. Yeah? Assuming this balancing line as a problem, it is not obvious from the first moment that this is influencing the behavior of the thin loop, but as one key parameter. The system will show you this. It will show you that this parameter is influenced in different terms, how it is influenced by, for example, the nitrogen from the processor compressor, the speed shaft, the steam, the balancing line, in priorities. So this has the biggest influence, this has the lowest influence. This is what varied analysis means, yeah? And this is very helpful if you want to find a problem and you don't know the reason at the beginning. Yeah? We started this with one plant in Egypt for the initial model building. As I said, nine plants similar to each other, so it was the perfect spot. We prioritized the data. So we started with 30 million data points over 4 months. We analyzed them. We found patterns. The problem was that the plant itself was pretty stable, yeah, so it was not tripping every week, alhamdulillah. But we still found some interesting facts. So the basic model intelligence was confirmed. Here you can see, for example, this is one parameter. For example, I think this is the flash drum pressure. And you can see here from the patterns how the varied analysis sees what is influencing the flash drum pressure and the separation temperature. You can see here the main data. When you start analyzing an ammonia plant, for example, the most easiest way to see where's the stone wall is, you take the trip schedule or the alarm values and see how the data is approaching to these values. Yeah? So you take the PNIs, you characterize the most important data, and then you put the trip schedule behind it. Yeah? The trip schedule will show you always when is the data normal, when it gets critical, this means in alarm range, and when it is tripping. Yeah? And the more closer the data gets to the alarm or to the trip, the more in advance you have to act. Yes? So for example, you can see here, this is a value where the plant, for example, is operating stably, but it's still in alarm conditions. Yeah? This is the reformer box pressure, a very difficult parameter to control because it depends on the fan speed, the flap and all of this. Yeah? But it's an alarm. Yeah? Even if that everybody thinks it's running normally, one small disturbance it might trip the reformer. And tripping the reformer means we're tripping the whole plant. Yeah? Or for example here, yeah, this was the indicator for a back-end trip. Yeah? Because the suction pressure of the refrigeration machine suddenly came too low. Yeah? All of this can be derived. What is also possible is that you can, with the software, you can also compare trip scenarios to each other. As I said before, it is not a problem for experienced plant operators to detect a trip, to know why the plant has tripped is also easily. But if you have, let's say, I don't want to say something bad, let's say you have 2 trips or 3 trips a year because of, let me call it maloperation, yeah, for example, yeah. You can compare them to each other. On all parameter basis, you can see the history before the trip, what happened during the trip, and before, and what was the consequence out of this, yeah? What was the reaction when the trip came? So it is possible to compare trips also towards each other, which is also very important to see what were the behavior patterns out of these trips. I know it's not obviously important to do it when the plant has been tripped already, but it is good to prevent sometimes trips in the future, because I have seen it that the same trip came in 3 months 2 times or 3 times, yeah, and every time they say it was instrumentation fault or it was it's Ude's fault. Okay, it's always Ude's fault. I know this, yeah, but in this case at the end it was because of a maloperation. We found it, yeah, by using such a behavior analysis, yeah. So, in principle, it's comparable to the electrolysis. We did the same. We took the 30 million data points. We filtered them because there's a lot of this data which is bad PV or which are, the instruments are not calibrated for a long time, so you cannot use them. You take them out. You reduce the dimension because, let me say, the condensate temperature is not, this has not the same importance as the reformer outer temperature. Yeah? So you reduce the amount of important parameters to save calculation time, yeah? Because running in a whole ammonia plant is a very calculation-intensive process. So you reduce the parameters to the most important parameters. You do a clustering model. You see what parameters are going away from the normal curve, and you cluster them and build agglomerative models. And by this, at the end, you are able to classify plant conditions. For example, you can see here the blue ones is normal operation. Everything is fine. See? The red ones is a plant trip state. This means the plant has tripped. This plant here, for example, has not tripped totally. It was just a back-end trip. This means downstream of methanation, it has tripped. Yeah? So, here, this is the state upstream of the trip. And you can see already here that the plant is changing, the data is fluctuating. It is not directly obvious that the data is fluctuating, but this here at the end, this is a standard deviation. Yeah? This means, for example, let's say the fuel gas pressure is changing between 1.1 and 1.2. This is the normal behavior. And later it's changing between 1.1 and 1.22. Nobody will recognize this, yeah? But if it's increasing from 1.22 to 1.25, 1.26, and all of the time, and then it's coming down back to 1 again, 1.27, back to 1, 1.28. So this fluctuation is changing the standard deviation of the numbers. And this will be recognized by the system. And from this, the different plant statuses are derived. So interacting with the data here, it's too late. So then the process is useless. You have to act here, from normal to yellow, because here something is changing. And then you have all the time here to find out what is changing to prevent the red one happen. This is the idea behind of it. So when you got a lot of data, you have to make a clustering. Yeah? We are using several models, mathematical models, and we have experts for this. Yeah? As I said, I don't know nothing about ammonia plants or urea plants or any about chemical processes, but they're good in numbers. Yeah? So they make an analysis. They can define the data points. They can see, is the plant behaving by a linearization in normal process, or it is starting to change. We are deviating from this green line. And they can cluster the data. As you can see here, the number of data points are clustered in different plant states automatically. We just read them, and we cluster them and say, okay, this plant statuses belong together, this is together, and this one belongs together. And this in terms of standard deviation. This is not showing anything about a process pressure or temperature or anything. It's just a standard deviation in the plant pattern. See how the plant is changing in its behavior. And the data, the reason why I've shown this picture is only to see that when we characterize this data, we just show them that the red one is the trip value, the green one is normal, and the yellow one is the alarm value. Yeah? So putting this data in this range, you can also see how the data is behaving. This means it might also happen that the data is fluctuating from yellow to green, yellow to green, yellow to green. Yeah, and this is the most important reason to find it. Yeah? If it's always green or always yellow, it's fine. If it's always yellow, then you know you have to do something about it, or you leave it and live with the risk. Yeah? For example, here, this reformer box pressure, if the valve is bad for the fan at the reforming section, you can do nothing against it. Yeah? They have to live with it. Yeah? Maybe it's a design error, you never know, yeah? But if it's always green, it's also fine. But it's dangerous if it's fluctuating between green, yellow, because then it might be also go to red, and then the plant is tripped. So this behavior analysis needs to be found out. Yeah, this, for example, was the reason. It might also, it's also possible, which I found out later, that the plant might have stopped manually. Yeah? They have stopped the plant manually, and also might this be the reason why the plant has been stopped, yeah? But in the first analysis of the data, it seems that the plant has been tripped because of a reason, yeah? And here, for example, is also a good example is this data, as you can see in the range, was done over a different amount of time. Here it is in 2 weeks, over 4 months in a 1 hour average. So analyzing a data in 1 hour average, and you see here, you think this is the reason why the plant has tripped. Yeah? Later I found out that you don't know if the plant has been tripped manually or by accident because the plant has tripped because of a failure. Because in 1 hour average you don't see anything. Yeah, this is why we took the same data for 1 minute average and we found out a little bit more detail what happened exactly. Yeah? So the data needs to be as fine as possible to get the biggest benefit out of it.
So just a bit how to check in the manual shutdown of the check plan.
The manual shutdown, the reason is pretty simple. If you see here, this is from October to March. It's 4 months. This is taken from the data historian, 1 hour average. In 1 hour average, you don't know what happens. But if you look in 1 minute average or 1 second, depends how fine you get it, then you will see it. If you look when you trip the plant and you look in the ESD, you don't look in 1 hour average, you see the milliseconds. You see automatically this was the first out and then happens this and this and this. To keep the plant safe, you need to find the same tuning. Yeah? 1 hour is useless. The whole idea is useless. You can see a catalyst behavior, catalyst efficiency can be done in 1 hour average. Because you see it's going slowly up and down, temperatures are changing. But if you want to predict a problem which might fail the plant, 1 second for most of the parameters is essential, or 1 minute. Yeah? What we recommend is the same scanning time the DCS is providing anyway, we would record the data. Because changing the scanning time might overload the DCS. This is not good. So the same scanning time the DCS is already, we would take the data and record it. This one is also a very nice picture because it shows you, for example, we took 28 trip parameters and the blue ones sees, for example, it means that this parameter here, you cannot read it, but it's fine, is strongly influencing this parameter here. This means the trip parameter is strongly influenced here by this parameter. And yellow means it's only a weak connection between these two. Yeah, this means it can show you which of the parameter most probably has the biggest influence on your critical parameters in the plant. Now I come to the last example what I have. We did it also for a pet plant. Yeah? And here it is important about the product quality. Yeah, as I said before, this I think can be applied in urea plants, for example, where according to my experience, the product quality is mainly measured by laboratory analysis. It's not online. Biohead content, nitrogen and distribution size, and all of this is done by discrete analysis. So here we had the same problem in this pet plant. We took the parameters. We had a strong influence over different parameters which had expert know-how. We had total data points. And at the end, it was the quality of the product which needs to be optimized in the process itself. So the idea behind of it is by integrating, for example, lab results. You scan them and you compare them to the operation data with the same time stamp. You can build an experience level. And you can make a connection between the operation parameters and the outcome of the product later. Yeah? And by this, you can make a probabilistic behavior analysis. If you change this parameter, it will affect the product quality in this direction. You can do this with an artificial neural network, which is a machine learning process. This means you can apply algorithms which they take the operation data, and you feed them with the lab analysis, you give them the target value, and the system is learning by itself how the operation parameters are influencing the product quality results. In the PET process, it worked pretty fine. Yeah? This means we took the process data, we normalized them, like always, we trained a neural network, and the training data went to this to a data transformation process again, and at the end, it fed the product quality data. So at the end, this one influenced this one, and backwards. And the trained neural network at the end helped us, this was pretty complicated, helped us at the end to find a connection between the product quality and the operation parameters, and by this way, they were able to change the operation data to optimize the product quality. I'm very curious to see if this works also in urea plant, for example, because this is my field. If this can also be applied, yeah, because in urea the critical parameters like bioret and nitrogen and hardness and the size distribution are also interesting parameters, and it is interesting to see if this will also work, yeah. But hopefully we will have a use case for this in the near future. And at the end, they were able to change or to optimize their product quality and to improve their profit. This is it. Thank you very much for your time. Yes.
My name is Alan Abu. That you mentioned in the whole parameter analysis that you get that million process data parameters. That and you reduce them based and you specify that you filter that is that how can your model will deal with these with the odd parameters which will impact the process and may cause a bigger problem for the math, because you eliminate some of the database on the operation of the.
Yes.
This is one question. And on the last slide you mentioned that to change and to optimize the process parameters inside that in order to optimize the product quality. For this, what will be the impact on the process and on the running cost of the process when you optimize these? Because you will lose. When you improve your quality, sometimes you will lose. And the running, you will lose and you will increase the running cost. Thank you.
Yes, thank you. So regarding the data filtering, the first thing you have always to do is when you get all of this data, you filter the data which are bad PVs anyway. Yeah, which are showing none on NN or bad PV, you filter them out. And after you filter them, you filter approximately, let's say it's 10% of the data which you cannot use. You see directly the instrument is not correct. Yeah, because it's impossible, or I have seen only a few plants where all of the instruments are maintained correctly. Yeah? Some of them are always going bad. Yeah? This you filter out. And then in the next step, you prioritize them. Yeah? You sit together with the process engineers from the plant and you discuss which are the most important parameters. As I said before, for example, if I'm looking for a condensate temperature, let's say turbine condensate temperature after the pump, it is an unimportant parameter. The conductivity of the turbine condensate is not unimportant, but the condensate temperature itself is unimportant. So you filter this out. Yeah? And you just focus on, let's say, from the 100%, 10% are bad, and let's say 10% or 15% maybe they are not. You can keep them out because they are not influencing them. If you go back on the varied analysis and see which key important parameters are influenced by these unimportant parameters, they have no effect. Then you filter them out. And the remaining 75, 80%, you run an analysis on them. Yeah? This is the easiest way to do it. Yeah? And the second thing is about the product quality. It depends. Yeah? The product quality, for example, in this example with the PET plant, the better the product was, the higher price they get. The better quality they had, the higher price they could sell it. Yeah, this is why I'm saying it's maybe different than in urea. Yeah, if here the example was it was good and they made it even better. But consider the following case: if it's not good, and you have to make it good enough that it works again. Yeah. For example, you are not achieving, for example, the bioret content in the urea, for example, yeah, or you're just hardly scratching the limit, yeah. the colleagues from Stomach Carbon can more explain it why the bioreactor is so important. So, and you optimize the plant that the bioreactor gets more stable, in a more stable range, that is still for fertilizer use possible. Yeah? Then it's not a question of running costs. Yeah? It's a question of keeping the product sellable at the end. Yeah? And in any case, what the outcome out of this is, you have the first idea is to change operating parameters. And the second step behind it, for example, changing operating parameters does not mean you need more feedstock or more utilities. And in the second step, it might become necessary that you increase steam consumption, for example, yeah? For stripping, for example, or something like this. Then, of course, your running cost gets higher. Yeah, it depends almost what's your need. Is your product good enough? You don't need all of this. Is the product bad and you need to increase it? You don't have a choice. If you find a customer who is willing to pay a higher price for a better product, it's also a good choice. Yeah? It depends on the use case you have.
We are spending money just to get PCS, get PLC, get this one to collect data. And we're forgetting the important part, which is predictive before predictive. That means we concentrate about the preventive and we treat our things and we make a procedure for things, how to be predicted and how to make analysis for the main cause of the problem.
Yes.
Then we write that we save a lot of money to go for further things, which, because sometimes we are spending money or to get devices, to get instrument for something which we could treat it.
Yes.
Easily.
Yes.
That's what my advice.
Your point is, all of this, if you do preventive maintenance or predictive maintenance, my colleague will have a presentation about of this correctly. All of this is not necessary.
That's it. That because the aim of every organization is the cost. Sometimes we are spending money for cost, like the companies which reducting costing. There are
yes, fully right. But okay, it's not. You cannot fully keep it out. Yeah, but you're right. Fully preventive. Yes, yes. But then, if you do preventive maintenance correctly, then you can focus on the efficiency of the plant here.
That's it. And you just concentrate about the analysis for the performance of those things.
This whole idea of data analysis and prediction and preventive is just a part. It is equally usable for maintenance and operation. Yeah, we do it for both parts. Yes. As I said in the presentation, a plant which is one day down, it is 1,000,000 times more worth it to keep it uptime than to make it efficient. Efficiency is the second highest priority. Even though I'm a process engineer, I would say efficiency is the most important thing. No, it's uptime. Yes. 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 Yes.
For the analyzing.
Yes.
What makes you encourage the customer to invest in your solution? Many plants have their own analytic department to make their cause analysis, make their own KPI.
Yes.
What is from the new system that you can make an added value to the plant?
Well, technically speaking, is that we combine your capabilities with ours, since we work together. Because we have the design know-how, and we have the mathematical know-how to analyze the data, even without knowing the process. Yeah, this is the key, yeah? That we found things in the plants without knowing what this data means. And then the process engineers are looking behind of it. And then the knowledge is combining between your operation experience and our design experience. This is from the technical point of view. From the business point of view, it is like a performance contracting. Yeah? I always suggest to the clients that there's a testing phase and you see the benefit out of it. This is what I'm proposing, because I cannot go to a plant which has not tripped in 450 days and say your plant is bad. It will not work like this, yeah? Yes, so. But if you analyze, if you give us the data, we analyze it, and let's say after a few months we come back and say we found this and this and this, and if you optimize this and this and this, it will, and you change it afterwards, and the plant is, for example, saving some normal cubic meters of gas, saving water, it's getting more efficient, for example, yeah? Or you found problems which you are acting in preventive, then you see a benefit. Then we can discuss about a certain business model behind of this, yeah? But technically, if there are plants in the world for sure who don't need us, yeah, I'm pretty sure, yeah. But I'm still here in this business because there are many plants they still need us, yeah. Yeah, it's not that we are focusing on your new plants. The service part in our company is as big as the new plants. Yeah, there's a lot of trouble in the plants ongoing, yeah. Good morning.
After the implementation of recommendation, any guarantees that this change in the process can be effective during the impact process?
You mean in
any guarantees for that company?
No, what we are not interacting with your system. I can.
I mean the recommendation itself that you are giving. We have to implement it in our plan to increase our product quality.
Yeah, for sure. So if we
any change in the process or in the product after that, any change, any bad impact, any guarantees?
I would say it depends. Anyway, you have to start one step before. I analyze the data for you. I file a report. Then I come to you and we sit together. And I say I found this and this and this, and I recommend you to do this and this and this. And then you say, yeah, I agree. Or you say, go away. I don't want to hear it.
If I agree and I implement.
Yes.
Then if any bad impact can be for the product, there is any guarantee for that?
I think we never discussed this topic before, but I think it can be, guarantees can be given, yeah. But the point is, if your plant makes a better profit, for example, yeah, then do I have a share on it? No, eh? Because the opposite is also the same time. I say you do this and this and this, and the plant most probably will not trip, most probably, yeah. And then the plant trips. Can you come to me and say, Tarek, the plant tripped, you owe me $1 million? No, it's not possible, yeah? Cannot do it. Yeah, for sure. I will be, if I install it, I will be from the process part, and then I have my IT guys, yeah, who are implementing this DCS specialist. I'm not a DCS specialist. And what I did in Egypt is, I took the device to Egypt, and I showed them the device. We explained the device, the connections, the DCS together, and discuss about the OPC, tie into the DCS, the effect on the DCS. The idea is the plant doesn't have to be stopped. It can be installed in a running plant. Yeah? If you have a regular turnaround coming, it's even better, for sure. Yeah? But this is the idea behind of it. Yeah? But for sure we will be present, yeah. But I will come also without installing it, just to visit you, no problem, yeah? Shall I proceed? The next one? So in any case, if there are more questions, I think these presentations will be distributed later. Will you distribute these presentations later or not?
Yes, we will distribute it.
You will distribute it, okay. So
I think it's better to interact during the presentation.
Fine. Mr. Muhammad Ali is suggesting that if you have questions, just ask them in the middle and interrupt me. If this is easier for you. Well, between us, it's not a problem for me, yeah? So just interrupt and ask the question, no problem for me, okay? Good. The next topic I want to talk about, which is more conventional, yeah, is about revamping options in ammonia plant, yeah? We are in ThyssenKrupp, we are not building only new plants, we are also making services, and more important, we're making revamps, yeah? The biggest or the most famous revamp we did, I think you know the Safco 4 plant in Saudi Arabia, in Ruwais. It was in 2006 the biggest plant in the world with 3,300 tons a day. It was revamped to 3,700 or 670 metric tons per day. Yeah, so the project is nearly finished. So there are a lot of options which can be done in ammonia plants. And I have here a presentation which is, let's say, focused a little bit more on the conventional plants. A good use case is the Egyptian plant types, which we have here. It's with 1,200 ton plants. But it can also be applied on 2,000 tons, 3,000 tons, or even if you have bigger plants. Not a problem at all. This nice picture is for my last project where I was. It was in Dumyat, in northern Egypt. It's a double train plant, each one 1,200 tons. A very nice project, yeah? Long project, but very nice. So I will show you some introduction, what is possible. Then I will focus on the options which we have in the front end and the back end of the ammonia plants. I will focus a little on the utilities, especially in the water treatment, and at the end, how a revamp might be executed. So what are the targets of revamps? The most easy or the most common questions is always increase the capacity and save energy. Yeah? And typically both together. Make more product and save gas. Yeah? This is a big challenge always. Yeah? And improve the environmental conditions. Yeah? As I said, for example, in Egypt, they have a very strict environmental law there, which is forcing that old plants also might change their emissions behavior, their effluent behavior, to be conforming with the laws. Revamping an ammonia plant or an urea plant is much easier if the plant is a little bit older, yeah? Because most new ammonia plants, they already have the best available technologies and the margins are very low. You know that the contractors are forced to be cheaper and cheaper and cheaper to be competitive, and this means they reduce the margin. Honestly, yeah? If you look in ammonia plants 25 years ago and you look in the margin in the CO2 removal, it is much, much higher than today. Yeah? For example, if the plant has been revamped one time, it is hardly to revamp it a second time. Yeah? The challenge gets bigger and bigger and bigger. Although there are plants which has been revamped three times. Yeah? In Australia, I have seen one which was revamped 3 times. Yeah? But the costs are getting higher and higher and higher. Yeah? This is a typical scheme of an ammonia plant. Most of you know it. And I will focus now on the units, unit by unit, and how things can be applied. Looking on the options, I categorize them in terms of how can the capacity be increased or how can the energy be reduced, the energy consumption. For example, starting on the front end, changing the primary reformer catalyst. We all know the catalyst from the competitor, from the vendors, Johnson Matthey, Halter Topsoe, Clariant. They're all pretty much the same, quadroloop, octaloop. They have the similar shape. Yeah? A new way can be that you use Catacell, which is a foil-supported catalyst in the primary reformer. I will have a picture for this later. This for sure will make you capable of increasing the capacity of the plant and reduce the energy, yeah, because it will change the heat transfer is improved and the volume of it is improved. So this means you will come closer in principle to equilibrium. You can change the tube material and reduce the wall thickness. Yeah, instead of going from the conventional microalloy, you can go to micro R. This will for sure reduce the wall thickness and you can increase the inner diameter. Yeah, you can use gas turbines or fuel expanders, because what makes me always sad is when you have a battery limit conditions of 35, 40 bar, and then you come to the fuel system and you have a let-on valve. Yeah, this is pretty bad. Yeah, then when you just do 6 bars, then you lose all the energy from 35 to 6 bars. This can be used in an expander and help you generate, let's say, 700-800 kilowatts, for example. You can reduce the pressure drop in the CO shift, HT or radial, HT and LT to radial flow. This will dramatically reduce the pressure drop and save energy on the syngas compressor. In the CO2 systems, I have examples for both of them, Benfield and AMDR, or as a white, how is it called today. Focusing on the Benfield, you can change the activator, you can change the packing. You can install in MDR systems, you can introduce a low flash, yeah, which helps you also to get more CO2 of the solution, reduce the reboiler duty. You can for sure do a balancing plant, which is consuming a lot of natural gas. For example, by bypassing, by introducing an additional amount of natural gas to the CO2 removal, and then removing after the absorber the natural gas back as a form of fuel and consuming the CO2. Yeah? This is especially interesting for plants who don't want to make any ammonia surplus. Yeah? Or you can do a CO2 removal from the flue gas. It's also a valid option, but it's quite expensive. This is the problem. Yeah? There are solutions available from MHI, for example, or from Alstom, or even from TKS. But this is a very, very expensive solution, but it's possible. In the back end, it's always a good idea to install a drying unit. It will save you refrigeration duty. Synthesis gas chillers, interstage chillers are a good idea. Yeah, but this needs to be combined, yeah, because at the end, if you install chillers between the syngas compressor stages, you will reduce the syngas compressor duty, but you will increase the refrigeration compressor duty. So these compressors always are keeping the balance to each other. Yeah. So if you want to install a chiller in the syngas compressor duty, install a synthesis gas drying unit also, because then at the end you have a good compromise in energy consumption. You can change the catalyst in the ammonia converter to a high active catalyst. Most of you know it maybe. For example, the Johnson Matthey, it's called 7041. We are using it, we have good experience with this, in the 100 bar ammonia synthesis. I will come to this later. And you know the product from our competitors, from Amomax, from Suchimi, you know it maybe. It is also a very high active catalyst. You can install a booster converter in the syn loop. If you have only a 1 converter plant, you can put a second converter, or you can install a medium pressure ammonia synthesis, which is installed in our 3,300 tons plant, which runs at 100 bars, not at 200 bars. Yeah? I will show it in the presentation. And at the end, I would like to discuss something about ZLD. This is in case you have very strict water effluent rules, then a zero liquid discharge is always a good solution.
Do you have any percentage or numbers by how the capacity increase for the next can be reduced by different?
I will show you now. Not for all of them, but for most of them. Yeah. This is Catacell. This is a primary former catalyst. It looks like a toilet brush. I never said this loud, but it looks like a toilet brush. It is a foil supported. These are foils, and it's on a stamp, and you just put it like a brush into the tube, so it's easy to fill. It has a higher activity, a higher pressure, a higher heat transfer, and a lower pressure drop. Yeah, so this means at the end, it will help you to increase your capacity and keeps the energy consumption constant or reduce it. This is the flow pattern. As you can see, it comes from the top, and then it goes back in the radial direction. This is a product available at Johnson Matthey, the catalyst supplier, which is our partner. The detailed numbers, I have them, they're on my book, but the activity is approximately 20 to 30% higher. The heat transfer is approximately 20% higher, and the pressure drop is approximately 15% lower. This product is sold by Johnson Matthey and can be purchased by from them. Then we can look on the reformer tubes, which are designed normally for 100,000. It has not been used in ammonia plants. It has been used in, I think, in gas to liquid plants. They have used it, but it's not in ammonia plants used until now. No, not now until now. No, it's a new product, but it has been used in other industries. Yeah. But we have still. It is a relatively expensive product, but it is still the foil is the nickel oxide is on the foil, so the catalyst material is the same. So it is sprayed on the foil, the nickel oxide catalyst, and then we have many consumers who are planning to install it. Yeah.
So it is a recommendation, a new one. Nobody has used it.
No.
Are you recommending that for ammonia?
Yes. Yes.
But where does it be used? Where do we have an experience of that?
In other industries, like for example in gas to liquid and all of this. In gas to liquid, in other chemical processes, not in ammonia. They're just. It's like the autothermal reformer. Yeah, it just came from other industries to the ammonia. Yeah, so now it is a newly developed product, which we here just promoting it here and say this will offer you a good revamp options in terms of not replacing or not adding tubes in the reformer, for example. Yeah, because if you want to increase the primary reformer, you have to add tubes, you have to make bigger tubes, and this is a good option to save all of this. Yeah. And as I said, the base material is the same, so the catalyst is the same, it's still nickel based on a different base material, so it will for sure crack the gas like the other one also. Yeah, the result will be the same.
Do you think it could be applied in the ammonia?
Yes.
I mean, it doesn't need to change the dimension of the tube, because I saw that in more complicated to get it in the same.
No. We are recommending to change the tubes because of other reasons. But if you have normal tubes, for example, in Egypt we have this normal 5-inch tubes, this 127 millimeters, you can put it inside. They can make it in sizes which you prefer in this case. Yeah? And this will allow you to increase the catalyst volume dramatically. Yeah? But of course it is more expensive than the regular one. Yeah? It is better but more expensive. Yeah? Yes. But prices will come down. It is good. Then reformer tubes. As I said before, the reforming tube lifetime is 100,000 hours. Each of you know this. Who are dealing with reforming sections? So we are recommending to change from micro Li to micro R. Yeah? We have good experience with this tube material. It was implemented, for example, in the Safco revamp. It has a reduced wall thickness at the same mechanical strength, which allows you at the end to increase the inner diameter of the tube, and by this you can put more catalyst, even if it's a conventional one. You can put more inside at the same thermal stability. And now, coming back to the numbers, this is the original design of a tube. It's 100% capacity. You put the catacell in, you reduce the pressure drop by 22%, at the same catalyst volume. By replacing the tube material, the pressure drop reduced to 88%, but the catalyst volume increases to 107%. Coming now to our revamp case, where you have 110% capacity, without replacement, the pressure drop increased to 120%. At 100% catalyst volume for sure, because there's no more space in the tubes. If you replace the catalyst to catacell, the capacity can increase to 120%, with a moderate increase in the pressure drop, and the tube volume is the same. But if you replace the catalyst tube material also, or even better if you combine them, at the end you can reach 125% capacity with nearly the same pressure drop like in the conventional plant, and the catalyst volume has been increased by 7%. So this is hard to achieve because other parts in the plants are also affected from this 125%. But somewhere between this and here, you will go at the end. Yeah. So the pressure drop will come down to 90%, and even the catalyst volume will go to 105%, something like this, which is very good in saving energy and putting more catalyst volume inside. Yeah. This one, changing reformer tubes, is only applicable if the reformer tubes are finished anyway. Yeah? There are nearly no cases which we have seen where out of nothing we change 200 tubes of reformer or 400 tubes of reformer. They need to finish in their lifetime. Yeah? So a revamp is always a good idea when the reformer tubes are finished. But still, changing reformer tubes is a big effort. Yeah? You know better than me. Yeah? Cutting, welding, you have a short time schedule. Yeah? Turnaround is not that long. So it's a hard work. Yeah? For example, in the Safco revamp, we changed all the reformer tubes to this new material, and there were 408 tubes in the reformer. So it was a day and night job. Yeah? Alternatives could be installing a pre-reformer, for example. For a moderate increase of syngas generation, you have a moderate a pre-reformer, which is installed upstream of the primary reformer. It gets preheated, and then the gas is partly reformed already here. There are two things which are important. The reformer here needs a temperature approximately of 500 degrees C for the pre-reformer. So this heat needs to be taken from somewhere. So if you take it from the convection section. This is the most easiest way. Take it from the convection section, use the reformer and put it back to the convection section, and then to the primary reformer, which applies that you have to change the convection section, and you have to put a coil in between. And the second point is, if the gas is lean, if you have a gas with 96-97% of CH4, then a primary reformer is not the best solution. If you have a heavy gas, here in the Middle East I see we have more heavy gas here. In Egypt, for example, we have lean gas. If you have heavy gas, more C2, more C3, then this is an applicable solution. Yeah? If you preheat the pre-reformer with a fired heater, then forget the idea, because it's waste of gas. Yeah, better use it by energy recovery and put it in the convection section, which is of course a change in the convection section itself, because you have to cut and install a second coil in between. An alternative would be installing a gas heated reformer. This is a very nice solution if you want to increase your plant capacity and don't want to increase your steam export. Because if you have integrated complexes where the ammonia plant doesn't need to work as a steam factory, which most ammonia plants do, and if you have, for example, you have standalone ammonia plants with phosphate plants behind it or something like this, then the steam export is not that important from the ammonia plant itself. And the gas heated reformer is a very good solution to save that. So the idea is principally the same. We preheat the media up to, let's say, same like here, 500, 600 degrees. We go, and it is reformed parallel to the existing primary reformer. It got its heat from a secondary reformer. I have put here a second one to make it more clear. So the reformed gas is going out into the secondary reformer. You put the air, it's getting hot, and the hot gas out of the secondary is heating the reforming tubes into the gas heated reformer. And by this, the system is feeding itself. And at the end, what comes out from this gas, which is going out, at the end, will not that have much heat left to generate so much steam. Yeah, and the gas to the steam to carbon ratio is pretty high here. It's up to 4.5. So also the risk of metal dusting is pretty low. So it is a proven technology which has been used in Johnson Matthey old ICI plants, and they're running perfectly fine. You need something here to heat it up, like a fired heater or something like this. You need this. If this system is not running, you need here an external heat source to make it initially hot. Yes, yes. Yes. No, at the beginning, what will happen is you will preheat it here manually, or you take a hot effluent from the convection section, which is downstream flue gas side from here. You split it, then you have it hot enough to be here. It will not react here. It will not react, probably. And then you will anyway. You will mix it from here and even here. You have a high methane content. You will ignite it, and then you will start it up. But it needs a manual starter. It needs a manual starter to start it. Yeah, it's like for ammonia converter. Yeah. The most easiest way is it's like for when you have two syntheses. You start this one first, and you use the heat and the energy from the upper part, and then start the lower part. Yeah. So I put here two secondary reformers. But in principle, if the reformer is big enough, you can use also the same here. And then if this one is running, you can also this one is easy, and then you can ignite this one also very easily. Yeah.
What will be the outlet temperature of the gas going to the preheater expected?
This one?
No, the upper one.
This one?
So the outlet gas stream?
This one? Or this one?
Exactly.
This one will be approximately, yeah, it will be approximately 450, something like this.
So does that mean the system itself is self-heating up? I mean, the energy required for reforming is self-generated?
The feed steam preheating is self-sufficient. The feed steam preheating, yes. Yes, yeah. Because here, what we have here is normally you take it upstream of the convection section. This means you have here between 370 and 400 and something like this, and you come out here with 500 and something, 540. Yeah. So it is acting of a pinch approximately of 30 degrees. Yeah. Then the last one, which is very nice in terms of getting big increase of syngas production, is using an autothermal reformer. For you who are working in methanol plants or no methanol plants, the big methanol plants are all of them nearly today working with autothermal reformers. It's a much cheaper solution which can generate very high amount of syngas, and it's a good opportunity to replace or to shift or to take a part of the production out from the conventional primary reformer, because changing a primary reformer is a complicated procedure. So this autothermal reformer, in principle, if you put this in mind, what we had here, it is comparable, but here also the feed steam mixing is introduced, and it's acting like a primary and secondary reformer in one vessel. Yeah, and it can be combined again also with an auxiliary feed steam preheater. It has a processor adding, like the same like here, but since the reforming duty is much higher if you put pure air, then you have too much nitrogen upstream of the methanation. Yeah, because you have to reform, the reforming duty or the amount of heat you have to put here, if you leave the air separation unit out, which is possible, and you put only by air, to get a methane outlet here of 0.3%, something like this, which means that there's, at the end, when it comes out here, there's too much nitrogen in the gas for the ratio in the syn loop. And the firing in the reformers itself is a little bit more complicated because of carbon formation at the end. But it can be handled. But then at the end you have to put a PSA upstream of the methanation unit to take the additional nitrogen out. Or you put an air separation unit, which is common, for example, in methanol plants. And we have also seen it in ammonia plants. And you fire it by enriched air. Yeah, you increase the amount of oxygen in the process air to 23, 24%. It depends on the compressor supplier. Because, you know, if you increase the oxygen amount in the air too much, you get a problem with the oil and the bearings and all of this. Yeah? So this would be a possible solution. And it doesn't need to be a cryogenic unit. You can also put a membrane unit, for example, here, which increases for you, but then you need an additional compressor. Yeah? There are solutions today available. You compress the air, you push it to the membrane, and then the oxygen which comes out from the membrane is on the low pressure side. And then this low pressure nitrogen and low pressure oxygen is fed to this compressor and mixed with the normal air from the ambient, and then introduced into the reactor. This is a much cheaper solution than the cryogenic one. But of course the cryogenic one is more efficient. Yeah? The quality of the oxygen is better and the pressure is higher. But it's more expensive. Yeah? So these are alternative solutions to the primary reformer modification. Coming on to the CO shift. This is an example how a radial LT shift can look like. It is in principle comparable to a radial bed of the ammonia converter. It has a tube basket. You can consider this is a ring, a distribution ring. And then there are tubes. And these tubes, they are perforated with holes. And around these tubes is the catalyst. And then the gas flows into the tubes and then into the catalyst but in radial direction and goes from an outlet tube outside, which reduces the pressure dramatically and saves energy on the syngas compressor.
Could you show us the original for the
This one?
change? The symbol. The direction. The gear.
No, before it was the conventional configuration is axial. This means the gas comes inside, streams through the bed in this direction, and then at the outlet goes out.
What are the changes to make that difference, change the flow direction?
In an Egyptian plant, for example, in the typical Ude Egyptian plants, you just take out the two internal beds, and you install it inside the ring and the tubes, and it comes in segments. So it was our intention to keep the pressure vessel unchanged. Just take out the support grid and the catalyst, and install this ring and the tubes, and that's it. Yeah? More. Because there's a part of in the radial form that we can because the distribution we can a little bit higher. We will fill it to a higher level. So the active catalyst volume, total volume is the same because the vessel is the same. Yeah. If I build a new vessel, then I'm free anyway. I can put as much catalyst as I want. But if I have an existing vessel, then the total volume is the same. I cannot change it. But the active volume becomes more. Because in the yes, but the tubes are only on the outside. They are small tubes. If you have a conventional axial reactor, which has also a grid, a support grid, and you have the balls upstream and down and upstream, so this will be lowered. So the total active volume will become more. Yeah? Yes.
Won't it affect the highly extended
No. Why?
The new kind of this geometry, like the ammonia converter has quench to control the atmosphere.
It does need a quench. No. This catalyst is not that aggressive. It does need a quench. Yes, but at the end, it will not. It will come far to equilibrium. It will come close to equilibrium, and what then? So this will not go by itself to 260 or 250. It will stay at 220 or something like this, 240, 230. So there's no need to control it. Yeah, the behavior of the flow is exactly the same like the axial one. Yeah, because at the end the remaining time in the reactor is not that much different. The flow pattern is chosen like this, that the remaining time, the residence time in the reactor, is in principle very close to the existing one. But we did it because of the pressure drop. Pressure drop is the problem. Always in the CO shift, the pressure drop is the biggest problem. Yeah? You will not see it in the syngas compressor because it has reserves, but you see it in the consumption. Yeah? When we design the plant, we always consider a reserve in the front end as a pressure drop to keep the machine safe that it can still operate. But in reality, if you design the reactor with 0.4 or 0.3 and it goes up to 0.7, this 0.4 bar is affecting the syngas compressor and steam, for sure. And this was the reason why we did it. Yeah? Yes. No, we changed the internals. No, we don't change the pressure vessel. But the internals out, all of them. Completely. All new internals. Yes. They are anyway the same. It's just different catalyst. CO2 removal. CO2 removal, we have, I would start with the Benfield. The first point is, of course, it is for very old Benfield systems, yeah, because most of the people I know who have Benfields, they already changed from DEA to Act 1 as an activator. This is, but we still put it in because not all of them has changed. And of course, we recommend to put a high performance packing for a capacity increase. Yeah, it's just a packing with a better surface distribution, which will allow you to increase the capacity of the plant. So by this, 15% is possible. Another one is, as I said before, here this is our baseline, 1,200 metric tons, urea 1925. If we increase the natural gas feed, we increase the CO2 output, and after the CO2 removal, we take it back as syngas as a form of fuel. Yeah? This has been implemented in Egypt, for example. It was done in one plant, EMPC was done. It is also done in Fertil. We did it there because there was no ammonia surplus allowed. Yeah? So they want to keep the ammonia tank storage level as low as possible. So this was one option. The second one is you can do it by CO2 recovery from the flue gas. It is a conventional washing system. This can either be done by the MHI solution, which is using a solvent that's called K1. It is a very, very well-known and proven system. It can also be done by ammonia water, which is also a possibility, that you wash the CO2 out by washing it by ammonia water. And then the CO2 can directly be pumped to 150 bar liquid, and then it is dissolved from the ammonia water solution. Yeah. The idea can be thought also more far away, but then this will affect also the urea plant if you can also directly put the ammonia and the CO2, which will form carbamate or ammonium carbonate, directly in the urea plant. But this is a very advanced concept which requires a lot of changes. But the most easiest way is to wash it out, compress it liquid, and then dissolve it at a high pressure and release the CO2 for the urea plant. But it's an expensive solution, but it's a possibility. Here we have a comparison for both of them. What is available? What can be done? Yeah. So we recommend that for larger CO2 capacity increases, to wash it from the flue gas, and for moderate ones, just make the balancing solution. And will also improve the flames of your reformer. Yeah? If you have put more syngas, like a tail gas, it makes the flames, as we know, they make them more blue and more like a candle. Yeah? And the impingement of the tubes will become lower. It's like increasing the tail gas amount. This is for an MDR system, or as a White House is called today. This is the conventional solution as we know it. We have the absorber, semi-lean stage, lean stage. It comes out, it flashes, HP flash. The flash gas goes to the reformer. It can even wash further. It got flashed, this is at 5 to 6 bars. Then it comes here to 1.5 to 2 bar. It goes in the LP flash section, and then the CO2 is released. And the solution is partly put back in the semi-lean part, or it is stripped to a higher purity and then put in the lean solution part. This is the conventional AMDR process as we know it. To increase it further now is if you put a low pressure section here. This means we take the solution out from here, from the low pressure flash, and there it is flashed to atmospheric pressure, 1 bar, 1 atmosphere, or even lower. And this pressure is generated by a compressor or a blower who's sucking the dissoluted CO2 out from this vessel. Yeah, so the game changer is this one, who's generating this low blow pressure. And by this one, it is possible to recover the CO2, which is remaining in the solution, and get a higher purity of the solution here, which at the end saves, of course, reboiler duty. You can lower the circulation rate, so it can relieve your pumps. You can increase the capacity, but it requires a machine with a motor or a turbine and an additional vessel. Yeah? So in principle, if you compare a Benfield and an MDR, then the nearly atmospheric flash pressure from the Benfield has been put in an MDR. It's a part of a combination. But it's a very, very good system with very promising results and helping this unit to perform much better for higher capacities. Now we're coming to the syngas compressor. As I said before, this is the conventional one we know. This is the makeup gas chiller. First stage, water cooler, separator, second stage, same, third stage, and recycle stage. We can install chillers, but as I said before, it will keep the balance between refrigeration duty and syngas compressor duty. So this, on the first view, is not a benefit directly, because what you save here, you put in the refrigeration machine. But if you put a drying unit, what will be the effect? You have the makeup gas chiller as before here. Downstream of the first stage, you put a second chiller, and then you have a mold sieve drying unit, which will take out the water from the syngas. Instead of, because of the conventional way is, without a drying unit is, the remaining water in the syngas will be removed with the ammonia product later in the syn loop. This is how we know it. Here, the gas at the outlet of this unit will become dry. This means a dry gas can be also introduced on a different point of in the syn loop. Now, in the conventional way, the makeup gas is combined with the loop gas upstream of the separator, and here the water is removed, and then it's circulating. Okay? By using a drying unit, it comes down to here. This means the makeup gas is directly mixed with the inlet of the recycled stage and then goes to the ammonia converter. By this way, the ammonia content at the inlet of the ammonia converter is changed from, let's say, 4% to 2%, which makes the ammonia content between outlet and inlet of the ammonia converter bigger. This means the catalyst becomes, forgive me my word, more hungry. And at the same time, the chiller here is relieved. Yeah, so this is a very, very easy method to improve the syn loop. And we have good experience with this. Yeah? It is implemented in all our big plants, because in the big plants, I will show it later, there's an ammonia converter between this stage and this stage, intermediate ammonia converter. Yes, please. I didn't understand, sorry. Yes, but the chilling is consuming energy. Yeah, so if you're not forced, normally the gases, there are two chillers here. The drawing is not fully good. There are two chillers here, and the gas introduced between the two chillers, and then the makeup gas is cooled down, and then the water is removed here by the ammonia product. This is the normal way we do it.
I'm talking here, Dr. Chiller here.
This one?
Chill, yes. Not enough, because it's chilling here.
No, it's not enough.
It's doing the same when you chill. You
remove
the water.
At the first stage outlet, you have, let's say, 60 bar, 70 bar. And when you chill it down here, let's say to 4 degrees, it will not remove all of the water, because it's still saturated at 4 degrees. Molocatassive, adsorbent. Adsorbent, yeah, molocatassive. It is like a PSA. One part is adsorbing and one part is regenerating. And we're using for regenerating, you just reduce the pressure and make it hot. The idea is very simple. High pressure and low temperatures is adsorbing the water. Low pressures and high temperatures is desorbing the water. And for heating up, we're using the high temperature from the hydrogen removal unit. Just by passing it by, heating it up, and then going to the reformer.
Okay.
It's a good unit, very useful, but it requires good operation. We're keeping the levels on eye. Yeah? This is very important. Good. As I said before, a higher active catalyst can also help. Yeah, as you can see, this is the conventional catalyst, the typical magnetite catalyst from Johnson Matthey, which is 35.4, and we recommend to use 74.1, which has approximately 1.5 times higher activity, which will, in terms of outlet composition of an ammonia converter, increase the, I would say, from, let's say, 19% to 22% ammonia concentration outlet of the ammonia converter. This is our experience. And of course, with a higher ammonia concentration out of the converter, it will reduce the circulation flow, the recycle stage will be reduced, the load on the recycle will be reduced, and we can also keep the recycle flow at the same, and you get a higher product. Of course, you need more makeup gas, yeah, for sure. This is for plants who have only one converter, like in Egypt, for example. There, our typical convention is one converter with 3 beds. You can install here a booster converter with a second waste heat boiler. It is also possible to install only a second waste heat boiler if you have a problem with the waste heat boiler there. But what we could recommend is, this is one solution, or we install this one. This is, in our opinion, the best way to revamp a plant. It has also been done in Slovakia. There's 1,000-ton ammonia plant, and approximately this gives you 1/3 of the production. This was the first time installed in Safco in 2006, Saudi Arabia. The idea behind it is the following. In 2006, the biggest conventional ammonia plants were 2,000 tons. The syn loop was running at 200 bar for 2,000 tons a day. So our idea was that we keep the whole syn loop as it is. We don't change the equipment, nothing. We don't make it bigger. And the plant has 3,300 tons a day. So 1/3, we make it in this section. And this section is installed at 100 bar. This means out of the second stage, yeah, we have the drying unit, of course, for sure here, as I explained before. And then out of the second stage, there's a gas exchanger as a converter, which has no loop. It just goes through the converter, in and out. The waste heat is recovered. Gas cooler, chilling product out, approximately 1,300 tons. And from here to the third stage, to the syn loop, and then we make the remaining 2,000 tons. So this is a perfect revamp option because it will not affect your syn loop. You just put it between the compressor stages. Of course, you need to modify the compressor. Okay. But this is a well-proven at 100 bar running converter. And the catalyst we're using in this converter is this one. This catalyst has a very high activity at 100 bar. So now imagine this catalyst, which is already high active at 100 bar, how it will perform at 200 bar. So we have built a plant in Louisiana for CFI, Central Farmers Industry. This plant was designed for 3,300 tons per day. The plant is making 3,650 without any modification. Because they have just installed, they put some margins in the compressor when they designed it, and they have just installed this one, because it's from the initial design, and they put the high active catalyst in the syn loop also. And by this, they're making one world record after another. Any ammonia plant? Yes, here. This is ammonia. Where? Yes, 1,200 tons, 300 tons. It has this one is, in the conventional plants, it is a 3-bed converter, 3 beds, like in Egypt, with approximately 84 cubic meters of catalyst. And it's producing more than 1,000 tons. It has been implemented in SAFCO, in Marden 1, in Marden 2, and in CFI in USA. This is an UDE feature, which is, and we are now making a new initiative which allows us to go from 3,300. We made a revamp for 3,700, and now the biggest one we are offering is 4,750 tons per day ammonia. By changing the normal syn loop to 2 reactors with 4 beds and installing a 3-bed here. This means the normal loop can make 3,000 tons. Or 3,300 tons, and the intermediate step can make 1,450 tons. And references are available. This is also a very nice small feature, not unimportant, but who wants to save energy, it's a good, if you have a flue gas expander. Yeah? There are many plants who don't need a natural gas compressor because the battery limit natural gas is very high, 30, 40, 50 bar, yeah? And then what we see most of the time is that the fuel gas is just let down by a valve, by a PV, from 50 to 6 bar, and the energy is lost. This energy can be used in an expander, and by this you can increase approximately, let's say, 1 megawatt, 800 kilowatts, and you put this in a generator. And as you know, that 1 megawatt is approximately 4 tons of HP steam, then 4 tons of HP steam are saved, yeah? So it's a very good energy-saving measure. Then this is one of my favorites. The process compressor, for example, in the conventional way, allows you to make, if a typical steam system of an ammonia plant allows you to make a plant with 7 gigacal per tons production, consumption figure for the production. This means the process compressor is driven by a steam turbine. This can be changed, and for example, KBR is doing this also in their purifier concept, to a gas turbine. There are many solutions for the gas turbine to run it and to use the hot gases for the gas turbine, for example, to generate steam. This is the most easiest one. But you can also take the hot flue gases as combustion for the primary reformer. It's also possible. And by this, you can change the consumption figure of the plant to 6.4, from 6.9 to 6.4. And this is done because due to the simple fact that the hot flue gas from the gas turbine is for nothing. It's cheap. You get it anyway. It's just a simple utilization of waste heat, which can be good used in an ammonia plant. Yeah? The problem with this concept is this is hardly matching with no steam export. If you install such a system, then you need a strong steam demand behind it, urea plant and a power generation, for example, because the ammonia plant will become more and more to a steam factory installing this. But it is very energy saving, but it's expensive. But in terms of OPEX, it is one of the best solutions there existing. Water treatment, also a big problem. This is the conventional system what we have. Normally we have flocculator, water, sand filters, the mixed bed cation anion, including a cooling tower, and we propose to install a reverse osmosis at the end, so that this brine at the end will be evaporated in a crystallizer. For this crystallizer, you can see that only solid waste will come out, and the condensate and all of this will go to the cooling water system. And you can put nearly everything which comes out from the sand filters, from the anion and mixed bed, including from the cooling tower blowdown. It can all be treated in this unit. And for the crystallizer, there are several possibilities of energy which can be put inside. Yeah, you can evaporate them by sun. It's very space consuming, but it's possible. Electricity, which is rare, but the most easiest thing is LP steam, because it's available anyway. And by this way, you can reduce your liquid effluents to solid patterns, which can be, for little money, can be sold, and then you don't have the effluent problem anymore. This is one good solution. So when we have good experience, it's quite complicated in the operation, but from the terms of experience, it is good. So this is the final slide. So what are the phases to revamp a job? You make yourself familiar with the plant, which also requires that we get good data from the operation of the plant. Yeah, that we get good trends, good logbooks, well-maintained instruments, because you rely on these instruments, and if they are not maintained, you make false assumptions. You commence at basic and detailed engineering, and at the end, you make an erection and startup. And this, because it's our favorite example, we did it for our plants in Egypt, because there and there it becomes more and more requested from our clients, and as I said, the plants are pretty much the same. Thank you very much.
Good morning to you all. I am Sudeep Das from ThyssenKrupp Industrial Solutions. I come from the integrated asset management business, which is into operations and maintenance of different plants, including fertilizer plants. I thank AFA for giving us this opportunity to present about integrated condition monitoring to this respected gathering. Today we will discuss about some of the problems faced by the fertilizer industry in general. What is condition monitoring, how it influences reliability, how you can use condition monitoring, or you can assess the condition of your equipment using equipment performance monitoring as a tool. What should be the proper way of doing condition monitoring, and what should the organization look like, including the maintenance organization. And lastly, a few case studies of condition monitoring detecting problems in the fertilizer industry. In general, if you look at fertilizer industry, you will see that there is a lot of downtime due to unplanned failures. Planned and detectable problems are there, but at times there are unplanned failures. And of course, there are associated higher risks with HSE, and as a result, O&M costs will increase. So when we speak about condition monitoring technology, how do you deploy it on your assets? You cannot have one fits all. So in a plant, when you do the criticality analysis, you will have different equipments in different criticality categories based on environment, safety, maintenance cost, production rate, and any other factors which is very specific to that asset. So normally, depending upon the criticality of the assets and the PF curve, the point of potential failure and the point of actual failure, if that duration is in seconds, you have to deploy a online continuous monitoring system, which normally happens in case of critical assets. Similarly, for assets which are mid-critical or which are known as essential assets, you need to have transducers permanently installed, but the data is processed or collected at regular intervals, which is decided by the operator's experience and the OEM's recommendation. And for non-critical assets, you can use a portable data collector to collect various condition monitoring parameters. So the most important thing is the PF interval, which will guide whether you want to use an online continuous monitoring system or a portable device or a scanned surveillance system. The second important thing is in terms of criticality. Criticality drives maintenance strategy, and maintenance strategy will decide what condition monitoring parameters will be measured and analyzed. And the highest criticality assets represents the greatest operating risk to the business, so you spend more time and more resources to see that they are operating safely without any sudden failures. So this is a list of condition monitoring parameters. This is not really visible because of the number of parameters being high. I will share it separately, the Excel document, and you can see. But the purpose of displaying this list of parameters is that when we speak in terms of condition monitoring or predictive maintenance, we normally think in terms of mechanical assets and vibration monitoring and maybe oil condition monitoring. But condition monitoring also means monitoring the condition of all assets in your plant, including electrical assets as well as instrumentation assets. For example, a control valve or an intelligent pressure transmitter or a floater transmitter. Now, apart from, even for mechanical assets, apart from vibration and oil condition monitoring, there are other parameters available which can provide a lot of insight into your machines. For example, ultrasonic measurements. For example, thermal imaging. So you need to decide what all parameters you want to measure and analyze to detect impending faults in your assets. So this is another list which is about monitoring the health of different assets as well as the process as such. So you can do condition monitoring of the process also. Now, recent developments in condition monitoring. If you speak in terms of electrical assets, as per the research of EPRI, for high voltage motors, more than 50% of the faults are stator related. And also in low voltage motors, more than 30 to 35% faults are with respect to stator. But till now, there were no such technology available to detect those faults. You used to know about it post failure when you used to open up the motor and do detailed analysis. Today, a technology is available for automated electrical and mechanical fault identification for electrical motors and generators. This is something different from motor current signature analysis. Here, depending upon the nameplate details, a model of the motor is created and the system collects data for 10 days and learns about the different states of the motor. And later on, it compares the actual data along with the empirical data which is developed by the motor and tries to find out anomalies. And it can pinpoint quite a few mechanical faults as well as electrical faults with relating to the rotor or the stator of the motor. Another tool which is being used today is predictive analytics. As a condition monitoring tool, which my colleague Dr. Tariq Al-Havri has already spoken about. Now, condition monitoring is also being complemented with performance monitoring data. Normally for critical equipment trains like a gas turbine or a steam turbine driven multi-stage compressor, you will be measuring thermodynamic efficiency of the equipment train. That itself can give you insights about the condition of the machine also, and condition monitoring data should be complemented with performance monitoring data. For cross-country pipelines and say solar electricity generation plants, if you have to do inspection, if you try to do it manually, it takes a lot of time. Today, drones are being used to do thermal imaging and visual inspection of cross-country pipelines and solar plants, and slowly this is getting introduced into other manufacturing plants also. So, how reliability is affected by condition monitoring? When you are practicing condition monitoring, you are trying to achieve no sudden failures and zero breakdown. And if you can achieve that, then you can have increased revenue, production and profit, increased lifespan of the equipments. More number of starts and stops reduces the lifespan of the equipment trains. Reduction in maintenance cost. Apart from that, condition monitoring helps you in prioritizing your maintenance task. Once you know the severity of the problem, you decide which equipment to attend to at what stage. Optimization of stock levels. When you know something is going to fail, you can requisition for the specific stock required. You can also optimize preventive maintenance activities like lubricant replacement in a gearbox. Normally, OEM will say, replace the lubricant after X hours of operation. But if you are measuring the contamination level of the lubricant, it can be either way. You can find that the cleanliness level are no more as per the recommendations, so you decide to change the lubricant even before you achieve the X number of hours of operations. Or it can be other way around. After X number of hours of operations, you can find the lubricant as clean and you can decide to extend its life. Planning and scheduling of proactive maintenance activities. For example, if condition monitoring suggests that there is unbalance in a specific fan or blower, you can plan for that proactive maintenance activity of balancing of the fan rotor in your workshop with proper planning. So that's how condition monitoring helps you. Now, how performance monitoring or thermodynamic efficiency monitoring can help you in determining the condition of your equipments. If you take the case of an axial flow compressor or any other gas compressor, thermodynamic performance can help you in knowing the condition in terms of when fouling is happening. So if you know it beforehand, you can take necessary corrective actions. Differential pressure is monitored to assess conditions of filters. So this is also condition monitoring. We perhaps don't do it that regularly, but you can do so. Process variables are also monitored and analyzed to assess the performance of chemical processes. How should the maintenance organization look like in today's world? In the morning, my colleague has discussed about digitization. How do you build it into the maintenance organization? You will have different systems like the condition monitoring software, a visualization tool. You can also have a predictive analytics platform. And nowadays, many OEMs provide remote services for monitoring their equipment trains. So all data is collated at a single source in your plant, and from there it is transmitted and transferred to a industrial cloud. Now many people have their own reservations in transferring this data to an industrial cloud with respect to cybersecurity and the data getting shared with sources where they shouldn't go. If you are a multi-locational plant, you can have your own private cloud, or you can tie up with an organization like Microsoft to manage your cloud for yourself. So it is possible today. And that data in the cloud will also be analyzed by the predictive analytics platform to let you know what is going wrong in your equipment trains as well as the whole manufacturing process. And this can also be extended to asset performance monitoring, wherein you, in order to predict the health of your assets, you are referring to all the parameters which are being monitored on your equipments. Now, what do I mean by that? For example, in every shift, the operator goes and notes down a lot of parameters in their logbook. It's a physical logbook. But whenever you are trying to predict something about the health of your assets, you are not referring to that data. If the same is digitized, for example, instead of the logbook, it's an industrial mobile which is intrinsically safe, and the list appears on the screen of the mobile and the operator just goes on saying yes or no, that same data can go to the integrated data source, and there it can be used to predict the health of your machine. So whatsoever data you collect in your plant should be taken into consideration to decide the health of your assets. Now, earlier I was speaking about integrated condition monitoring, how the organization should look like. But what should be the infrastructure of an integrated condition monitoring platform? First thing, it should be able to communicate with different condition monitoring platforms, as I discussed earlier, not only with respect to vibration, but other sources of condition monitoring data. For example, data coming from an electrical condition monitoring system, data coming from a control valve analysis system, then data coming from systems which will monitor your static assets. for example, heat exchangers, condensers. Normally, they can also be included in our condition monitoring program. Apart from that, the condition monitoring platform should have the ability to communicate with your enterprise resource planning software, because you need to generate work orders based on the results of condition monitoring, and the best thing to do is close the loop, whether the corrective action when completed, whether it has produced the necessary results. What do I mean by that? Condition monitoring says that misalignment is there in your equipment train. So you plan for an alignment job, and when alignment is done, you cross-check and you report that post-alignment, alignment is now proper. That should get reported into a enterprise resource planning platform or a maintenance management platform, whichever you are using in your plant. It should also provide you the ability to give access to OEMs to your asset data, based on which they can analyze the data from a remote location and provide you a second opinion about your asset. And lastly, what all feature sets you should look for in an integrated condition monitoring platform. Many people today include calibration management of all assets, not only mechanical things, all measurements which you are making in the plant, all the transducers, all the digital signal processing units, how and when they should be calibrated. It is recorded and maintained in the same system. The system should also be able to send you a message through either a text or an email that there are so-and-so alarms. For example, if at 2 in the morning you have high levels of high axial shift on a compressor, people who are associated with decision making of keep running the compressor or taking a shutdown should be informed immediately, instead of somebody seeing it on the screen of an HMI and then trying to call up somebody. Now coming to a few case studies. This is the first one is about a gas processing compressor, and on this compressor, apart from monitoring vibration, axial thrust and other things, predictive analytics platform is also going through the data using a model and trying to know what is going wrong. So all the operating conditions of the compressors and the associated system. So when we speak in terms of predictive analytics, it's not only the equipment train, but the associated systems like the cooling circuit, the lubricating circuit, they should also be included. So it was found that there were periods when the suction coolers were unable to keep up with the needed heat transfer, and this resulted in liquid carryover. So entrainment of liquids at times, if it happens a number of times, say it has happened 7 or 8 times, then fouling can happen in your compressor, and that fouling can also be predicted by the performance monitoring system. So if you combine both, you can come to know that liquid carryover is taking place, and if you look at pattern recognition, by looking at the pattern when fouling has happened the last time, the system can tell you that liquid carryover has taken place and fouling is going to happen most probably in this many number of days or weeks. So you can use predictive analytics and performance monitoring to predict what is going wrong in your equipments. Now, there are a category of equipments which doesn't qualify for online monitoring of different condition monitoring parameters, but because of HSE requirements, you need to monitor them. So as I discussed earlier, a scanned monitoring system can be used. Now in a plant, specifically in an operating plant, installing a new system and routing cables up to the control room at times can be a problem. So there you can use wireless routers to convey the signal from field to the control room so that you get the data and it gets communicated to the same integrated condition monitoring platform. And routers are available which can throw data up to 30 kilometers. And these are routers which are used in electrical distribution also, where data is being communicated from one mountain top to another mountain top. And it is very secured, the same level of security which is used in your debit or credit cards. And you can build redundancy also, 2 transmitters and 2 receivers. And one of the features which these have is that when the receiver receives the signal, it sends the feedback to the transmitter that I have received the packets of data. And only when that acknowledgement is received, data at the transmitter level is deleted. So there is no scope of data getting missed. And with this kind of a system, lot of essential assets are now being monitored. In India, from where I come, a few refineries are using this kind of systems because they have a number of pumps which are redundant and which does not require online monitoring, but they need to do condition monitoring. Instead of trying to measure data with a handheld device, they are doing it with a scanned surveillance system. Many a times when you are coming up with a new plant, you have a machinery protection system which will normally measure vibration, axial thrust, temperature, and at times a few points of differential pressure. To keep cost of the project within limits, a condition monitoring platform is not envisaged. So the machinery protection system is measuring all the data, but it is not being analyzed and transformed into information. But if you have a condition monitoring platform or software associated with a machinery protection system, it helps in a big way. This is an example. A compressor was running with high radial vibrations and it was above alarm limits but below the trip limits. So it's pretty scary and dangerous that at any moment vibrations can increase, cross the trip levels, and the machine will trip. And it was away from a shutdown which was 90 days down the line for an overall. Since the condition monitoring software was there, it was monitored closely and people were able to run the machine for those 90 days. And when the data was analyzed in the condition monitoring software, it was found that the machine has unbalance. And when the shutdown happened and people inspected the machine, a part of the rotor mass was found broken off. So this is the way condition monitoring helps. Machinery protection should be taken to the next level of condition monitoring. You have the vibration, axial thrust, temperature, online. That's why I'm saying machinery protection system. A machinery protection system is normally an online system, and that helps. So you can have the machinery protection system just there, not connected to a condition monitoring software. So you can know something is going wrong, but you don't know what is going wrong and how severe it is. But if you want to know what is going wrong and how severe it is, you need to connect the machinery protection system to a condition monitoring software where you have all the data. Thank you.
في احدى الكمبرسرز سواء كانت سن غاز او ناتشرال غاز او اني اذر كومبرسر فايبريشن أريد من حضراتكم أن أسمع أحد وصل عنده الفايبريشن، وصل لديه الفايبريشن إلى حد أعلى من النورمال ولكنه أقل من التريب بوينت، ويحدثنا ما يعني قصة حصلت لديه في واحدة من هذه الكمبرسرز، وش قد استطاع، كم الوقت الذي استطاع أن يؤجل الشت داون نتيجة لهذا الفايبريشن. لأنه في كثير من الحالات كثير من المهندسين يتخوفون، وأول ما يصير عنده فايبريشن above the limit يروح للشت داون لقرارات تعتمد على مصدر القرار في الشيفت انجينير او خلينا نقول الديلي انجينير. فأحب أسمع من حضراتكم لأنه حتكون مهمة هذه القضية، وحصلت كثيرا، أنا أعرف حصلت كثيرا مشكلة الشت داون، أضاعت وقت كثير من وقت الإنتاج بسبب فايبريشن كان ممكن أن نشتغل عليه ل3 أشهر ونوصل إلى تايم مال التيرن اوفر أو أني نكست شت داون. ممكن أسمع قصة من أحدكم؟
والفايبريشن اللي عند 95 and we didn't stop the plant and we keep it running for more than 3 months but under observation, direct observation to the machine. And because sometimes the vibration which you have it's not real. Even for the two probes are there, but sometimes there are some other parameters you should follow them. And also we have to concentrate about the temperature, which has reached 105, still we could survive. We are not reached for when we reach 115, by our experience, even 115 up to certain time you can run with it, because the melting point for that white metal up to 120 you could manage with it. That means you don't have to stop the machine directly as soon as the increase, just you have to follow, make a proper analysis for your condition to protect your plant, and till you see, but to be controlled properly, make a trend for your reading, what sort of things has changed, not just directly to stop your plant. That's our, we reach it many times, not only for this, also for the syngas turbines, for syngas compressors, different stages. We didn't reach that one, and we keep it running till we, based on our previous experience, we understand what's going on and up to what certain limit we could run. And what sort of a frequency also?
And compares it with the preset levels. The moment the grid value is raised, it will trip the machine.
Yes.
Now, what do you do after that? Or should you allow such trips in your plant? The best thing to do is to have the condition monitoring platform that data is being rendered as a reliability engineer or a condition monitoring
Yes.
engineer is
Yes.
looking at the data.
Yes.
And giving the right status to operations, that even if vibration levels are right, very near to it, you can run the machine.
Yes.
Now, what can be the different scenarios where such thing happens? As I told, in this particular case, vibrations were high, but it never increased suddenly.
Yes.
In condition monitoring, you also do at the rate of change. If something has changed over
Yes, yes, that's right.
Critical machines are steam turbine or gas turbine driven compressor cranes or very high megawatt capacity driven machines, which normally has journal bearings with force lubrication. Apart from vibration and axial thrust, what you need to look at is the differential pressure.
Pressure, yes.
of the lubricants.
Yes. Yeah.
Because the moment the oil layer will not be maintained inside the bearings, that can create a much bigger problem.
That's it, yes.
Even the shaft can seize within the shaft journal can seize within the bearing. So you need to look at that. That's why I told that whatever parameters you are measuring on a particular equipment train, that needs to be monitored and analyzed by someone who knows how to.
Yes. Collecting the samples also very important for in this case. Collecting oil samples nearby the outlet of the bearing also very important. And we have to make access how to do that even for our plants, you see. In that case, you can 100% guarantee that you can run your equipment in the safe way. And also the oil condition, as you said, to be followed completely, oil sample day by day, and you have to concentrate on that point, and you have to focus on all the parameters nearby. Added to that, the differential pressure and many other factors. That's why we keep it nearly more than 3 months. We are running with the same condition, and the plant continuously. When we open it, we were in safe, only the bearing rub was there.
Yes, I agree with you. When I share the Excel sheet for the condition monitoring parameters, which should be monitored on a specific equipment train, you will see that I have mentioned oil condition monitoring, but that can be again categorized as basic test and advanced test. Basic test should be viscosity, pH level,
Yes.
time period,
Yeah.
and contamination as per ISO limits. Right?
Yeah.
Now, contamination plays a very major role.
Sure.
So whether you,
Sure.
from where you are collecting the
Oil sample.
is very important.
Very important, yes.
For example, if you want to know whether the filter has failed or not, if you collect a sample before the filter and the sample after the filter, you can immediately come to know whether the filter is working or not.
Yes.
And for very critical equipment trains today, online oil condition monitoring instrumentation
Yes,
is available.
yes.
So instead of measuring at the header, you should measure near the outlet and inlet of the oil bar for each and every bearing,
Yes.
so that you can localize where the problem is. Because if you know contamination is high, from where and tear is taking place, you need to know that from which bearing or
Yes.
from some other source, whether there is dust injection or not,
Yes.
whether the breather is working or not.
Yeah.
So you need to know that. So for expensive equipment trains,
Yes.
instead of collecting samples and doing tests, you can also have online contamination measurements.
Yeah. One more thing, you don't depend on the online equipment. We are normally using the offline equipment like Scout 100, 140, Emerson 30, 31, whatever, to monitor all the nearest area daily and to check all the parameters behind, all the equipment nearby, just the vessels, the bearing pedestal, everything, because all of that parameters will help you in your analysis for any specific change.
What you should do is that when you have instrumented your equipment train and you are getting higher levels of cell vibrations, I think that's the time when you can pick up your portable instrument and collect
More data nearby.
to localize from where the problem is.
Yes, because in the online equipment, sometimes there are some other factors, and we face that one. For example, one GH compressor, you'll find everything smooth, but when you come nearby the compressor, you'll find there is a little vibration. For example, the bearing pedestal, when it becomes loose, you don't have any other parameters that will show you, and you'll see all the monitoring. giving you a very good condition, but the reality not. But because the very good operator, he'll see there is change in the vibration nearby, and sometimes that one more severe rather than the Banti Nevada or online vibration probes.
That's why it takes your
Yes.
what the operator goes and says, you listen to it. That data should get integrated into your data source for predicting the health of your machines.
Yes.
Normally, the logbook is a good source of information, but somehow it is not consulted. Thank you.
Okay.
السلام عليكم ورحمة الله. مالك أيسر راشدي. أشكر الجميع الحضور هنا، وأشكر بالأخص شركتنا وآفا. اليوم بعرض study case about CO2 absorber gas inlet distributor replacement. Slightly it is old study case, but it is good to share with the others. First of all, I will talk about our company, UMUFCO. Then I will give you a brief about ammonia process flow diagram, and then about carbon dioxide removal section. Then we will go for the study case as replacing why we have replaced this gas inlet distributor. Our company is a shareholder between three companies. From Oman side as Oman Oil Company as a 50%, and from India side is IFCO and CRIPCO as 25%. Company is located in Sur, and now we have already running around 14 years. We have two trains of ammonia plant and urea plant. Each plant designed for 1,750 ton per day ammonia plant, and for urea plant is designed for 2,530 ton per day. Very fast I will explain about the process in ammonia plant. Maybe somebody will they have different process. So as you see, we have received the natural gas here. Some of the natural gas having a sulfur, so we have a sulfur removal section. And after that, we have add the steam for pre-reforming the natural gas. Reforming section having two primary and secondary reformer. In primary reformer, most of the natural gas will be reformed. In secondary reformer, we are adding a process air from the atmosphere, which is having the nitrogen we required it for the ammonia. After the secondary reformer, we will get the reformed natural gas, which will be containing hydrogen and carbon monoxide and carbon dioxide, nitrogen from the process air. In shift converter, we have low temperature and high temperature. We have two reactors here. This will convert CO to CO2. Then this will process gas will go to CO2 removal section. In CO2 removal section, we are using Gamarco Vitrocook solution, which is based on potassium carbonate to remove the CO2 from the process gas. This is a big section, but we will go for, after that, by removing the CO2, it will go to methanation. Methanator is simply that what is remaining from CO2, which is slipped from this section as a ppm. Our plant is around 500 to 1,000 ppm. We will convert it again to methane. So we will save the ammonia catalyst. After methanator, it will go for the steam gas compressor. We will compress the gas up to 200 bar, and this will go to the steam loop. Steam loop, it is simply it is ammonia converter and separation for the ammonia. Around 30% of the processed gas will be converted to ammonia, and we will separate it by cooling it and separate it. Ammonia, we can supply ammonia to urea plant as 12 degree for urea plant, and for the ammonia storage we will reduce more temperature up to minus 33. This is about the ammonia process. Carbon dioxide removal section. This section containing absorber, this will absorb the CO2, and that solution which is absorb the CO2, it will go for 2 regenerator. One regenerator pressure is 1.1 bar, and the other regenerator is 0.1. We are using mainly Gmarkov-Vitrocook solution, which is potassium carbonate solution, and containing the DA, diethylamine, and vanadium pentoxide as a corrosion inhibitor. In beginning of the starting of the plant, we are making a rotation of solution, so that solution will form protection layer in all this system, because the system is mainly it is carbon steel system, and the packing is stainless steel. In absorber we have 4 packing material, 4 packing bed. Solution will came in 2 places. One place is, as we call it, lean solution in the top of the absorber, and the other part, around 15% of the solution came here, and around 85% of the solution came in the after the 2 bed. This solution normally it goes from the absorber, outlet of the absorber here. Here will be the gas inlet, process gas inlet distributor. Our study case about this point. As the solution is coming from the top and will become rest solution, and it will go and rotate again. Process gas will enter here in high flow, and this case, this is column database about absorber. It is packed column, and it's containing the GV solution and process gas. It's designed for 70 temperature here, and 115 and 150 as a temperature. As a pressure, normally operation pressure, we are running as 32 bar. Material, it is carbon steel material. Corrosion allowance for up to 3 mm. On 28 April 2013, iron increase in the GV solution. It increased up to 154. Normal iron we are maintaining between 70 to 100. If it is cross 100, there is something wrong, and we should take action, up to 100. So what we have taken action, we have add more vanadium pentoxide to the system, 200 kg fresh vanadium pentoxide to the GV system. In GV system, we have 2 things. One filtration system, and another thing is aeration tank. Aeration tank is simply a tank which GV solution which will go there and will add air to the GV solution to maintain the oxygen for vanadium pentoxide. So what we have done, we have increased the flow rate for the aeration from 9 up to 11 meter cube per hour. And we have increased the flow of air from 50 to 100 meter cube per hour. And GV solution temperature, normally we are maintaining in aeration as a 40 degree. So we have increased it up to 52 for more reaction for vanadium. Iron came down, and the system becomes slightly normalized up to 70 ppm. On 7th of May 2013, iron again increased, and it reached up to 172. So same action we have repeated, but we have added more vanadium. Vanadium, it is the main part for as a corrosion inhibitor for the system. But the iron still coming more and more. We have decided to check all internal towers in the next opportunity, and the next one came on 2014. We have a shutdown, long shutdown, so we got a chance to check all the system, and we have found that gas inlet distributor and absorber badly corroded. Many scenarios there, they are saying that it is corroded about vibration or things. But most of the things we have knows that as the corrosion layer inhibitor, that vanadium pentoxide layer wrapped off from that distributor, the corrosion started because it is carbon steel. When it is wrapped, so that start corrosion and continues corroded until that distributor badly damaged. There was slightly around the distributor found eroded, and we have checked by Larsen Tobro to check the thickness of the columns, and they're saying that it is normal, no effect there. Distributor above decided to replace by the stainless steel 316 in place of the carbon steel. This case happened in both plants. We have two trains. Both plants, same case happened, and mostly because of the wrapped of protection layer in the distributor. This is the old distributor. You can see this, the main part, header of the distributor, and this is the pipe which is coming from the distributor. It is totally corroded. After 2014, there was a shutdown on 2016, and we have checked again the new distributor, 316, and it was clearly no damage there, nothing there. Thank you for anything you can ask. After changing? Main things, this distributor, it is gas inlet for the absorber. As much there is a high flow of the process gas for that distributor. Most of the protection layer, which is in that distributor, it's wrapped off. When it is wrapped off, there will be a corrosion. And that because the solution, it is corroded solution. So it is continuous corroded and it is gone. Normally they are advised to stop the plant and start again to form the protection layer. But that it will take a long time. New preservation layer. Yeah, just a filter. That the normally we are cleaning the filter. We are cleaning filter for the mechanical part. But for the carbon filter, we are not doing the backwash for the carbon filter. But in this case, there was iron more in the system. So we have decided to backwash for the carbon. So most of the iron, which is will be absorbed by the carbon, activated carbon filter. No, the new one is SS316.
What about the rest of the process? Does the CES side affect it?
No, as the protection layer, preservation layer that in the system it is correctly, there will be no corrosion. Vanadium pentoxide normally it is in beginning of the plant. We are start for 36 hours. This formation of the layer will all system will be protected from the corrosion. System all it is carbon steel, and in beginning before starting the plant we are forming this layer by the reaction of vanadium pentoxide with the iron. So this layer will be formed in all the part of the GV area, and there will be no corrosion. As the iron increase in the GV by the lab analysis, we should increase more vanadium so that the layer will be form again. So any place will be damaged. Suppose there is vibration in any columns or any packing or something. So it will wrap that area. Corrosion will start. This will come directly in the lab analysis that there is some iron there. But as vanadium ratio, normally we are maintaining as 0.5 in the GV. So it will be form again that layer and there will be no corrosion. Foaming, yes, we are using anti-foam.
So during stainless or aluminum?
Which one?
Seeing gas.
Seeing gas.
You are using stainless steel labyrinth or aluminum, the material?
Stainless steel, that, yes, and seeing gas, that's something else.
No, I know, just
yes.
During the program, so the laboratory analysis showed that there is a consumption in the total vanadium number?
Yes, it came down. Yes, and we are keeping adding more.
And there is a more consumption?
And more consumption, yes. قصدك أنت during the shutdown of this case or 2004?
2004.
Yes.
So it's about
10 years.
10 years.
Yes. Yes, 10 years. And normally we are doing the checkout for all the columns during the shutdown. And for each plant we are doing the shutdown 2 years. So as it is 10 years, maybe we will take 5 shutdown, which checked for all the columns. We have many shutdown, but for checking all the columns, maybe around for each plant 5 times.
Change the design of the distributor or any material?
Distributor slightly design change. It was one big, the main part. This is the previous design. The header was one part. It is welded inside. And then the pipe it is coming out. But the new one, they have changed it to 3 parts. 1, 2, 3. Put it a flange for reassembly inside.
So you have 2 plants?
2 plants, yes. Same condition happened in the other plant. Almost 1 year between them. Yes.
It's probably of the design, bad design for
We cannot say that because total system it is carbon steel. So only this part which is having high velocity of process gas, it's creating corrosion. But the other part of the GV system, no corrosion there happen. Only the distributor. And there was no looseness in the bolt or anything like that. It is only directly corroded from the distributor. What do you mean?
I asked about analysis of problem. Why does Mr. Manjit correct after shutdown trip?
This GV system, only the process gas will come from process side. It will enter the absorber in high pressure, high velocity, and it will come out from the absorber. It will go to the process gas system. Remaining of the system is low pressure and low flow, not like inside the absorber. This is high flow of the process gas, which will enter through that distributor. Remaining of the part is lower pressure. So damage of the layer, it will be less. Any question? No, ask us. Ask us. Which? In our system, 5%. In our system, 5% of total GV solution normally goes to the filtration system. And that 5% is around 1500 meter cube per hour. 7 meter cube, it will go for the aeration. And that's it. And normally, daily, we are taking sample from lean solution, which is here. Before this bump, we are taking sample weekly, not daily, weekly, take sample for the iron and for vanadium and these things. 7 days, yes, weekly we are checking the iron. No, not daily. We are checking weekly for the iron. But during that case, we were doing more than 5 times per day to confirm that, because if you stop the plant for the iron, it is very difficult to find the source. We have many separator, we have many exchanger, we have many things in this loop. It is not here as a process. So to find that source of the iron, it is very difficult. So the plant was running continuous.
The Russian ring above the distributor.
Yes.
Is it a carbon steel or a stainless steel?
Stainless steel. This. You mean this one?
The one direct, yes.
This is the distributor here, and this is.
The direct, the Russian ring above directly above the distributor. What was the material?
I am not sure, but maybe stainless steel.
Because if it is carbon steel, then the iron is coming also from the carbon steel. So once you start corrosion in the distributor, then you will have the corrosion with the lowest flow of the.
Most of the system is carbon steel, except the packing. The packing is stainless steel. So, and we have changed the distributor to stainless steel. But the rest of the system, it is carbon. Maybe that you mentioned that because it is above the distributor, it will be affected.
بستعمل الطبقة الجوية تحتيها ستانلس ستيل والباقي كاربون ستيل ولا ستانلس ستيل؟ مهمة هذه القضية. هذه مهمة جدا عشان تصير في عملية الأستلايتنج هذا هيصير الكروجين يزيد نسبة الكروجين ستانلس ستيل مع الكاربون يبقى كأنه أنود راح يشتغل نسبة هيزيد نسبة the percentage of corrosion will increase as soon as stainless and carbon steel, like using a tattoo. Will be very fast. The corrosion will start very fast.
ما سمعك. Yes, as an activator. DA, he is diethylamine. Yes. It is, I have not talked about it, but it is mentioned there. Some of the things I am here. Glycine and diethylamine, it is as an activator, and V2O5 as a corrosion inhibitor. And normally we are checking for the vanadium pentoxide for the +4 and +5, and the total ratio between them is 0.5 we are maintaining. So that many plants they have changed and they have reduced the CO2 slip. But this is also costly, and this management part too decided to change it. We should change it. Okay, thank you.
Bismillah ar-Rahman ar-Rahim. Mr. Secretary General, our distinguished delegates, good afternoon. I would like to take this opportunity to thank our colleagues in OMIFCO for their hospitality, which something is not strange for our brother Omanis. And of course, we thank AFA for this wonderful event, and it is a fruitful gathering that sheds the light on knowledge sharing and experience exchange, which we hope everybody would at least go today out of this workshop or tomorrow with at least 1 point of benefit. Or if he did not benefit it, he would benefit the next guy sitting to him. So I will start by introducing myself. My name is Hamid Mohsen Dadi, mechanical engineer, graduated from Amman, Jordan. My Jordanian friends over here, brothers. And I do work as a loading shift supervisor at the Gulf Petrochemical Industries, GPIC Bahrain. And my presentation will be a little bit different because from morning people are speaking about vessels, temperatures, pressures, vibration, and all these. I'll be talking a little bit about the loading operations. May I know if we have anybody working at the export side of urea in the hall here? If anybody is there, just raise your hand. Excellent. Very good. So, so I can just unleash myself. Excellent. No, that will be very good. At least I'll be enjoying explaining what exactly we do in this part of the operation, because all the time people will be speaking about plants and the process, so we'll shed light at the end line of the operation. So this presentation agenda will be as follows. I'll start with a brief history. Good that we have a nice blend of backgrounds and cultures today. So I'll give a brief history about Bahraini pearls, since I like and love history. And I'll blend with it GPIC history. I'll try to make it a new way of an introduction. Then I'll give an overview for the handling and export section. Then the core of this presentation, the challenges and best practices. And I will wrap up with the conclusion. Questions, you are most welcome at any time. If you felt you need, or I'm available here until tomorrow, day after. So you feel free. So we'll start with the Bahraini pearls. Centuries ago, the island of Bahrain was one of the main hubs for pearls trade industry. So the whole community was structured in a way to fulfill and achieve this mission. So there was a group of people whom had the vision and had the resources and wanted to achieve the mission of pearls trade. So they used to sit around each other, assign the resources, plan for the voyage, distribute the roles and responsibilities, and eventually execute the operation. The nice thing that I want to point here is that after they return back and sell those precious pearls from the seabed, before going on the next voyage, they would again gather around each other and they will start having very important discussion. They will discuss what had gone wrong during post-voyage, how we can challenge or overcome those challenges that we faced, how we can optimize the resources, how we can reduce the cost, how we can eventually have a safer voyages and have a higher return on our pearls. So this defines unintentionally those people centuries ago were applying the best practice definition, maybe without having a proper definition for best practices, which is fabulous. Later on, with the Industrial Revolution, the oil and gas era started. And of course, in Bahrain in the late 20s and early 30s, oil was discovered, and those people started shifting from the pearl diving towards the oil and gas sector. So the Bahraini pearl started vanishing. Later on, in 1979, GPIC, the Gulf Petrochemical Industries Company, was established as a joint venture between three countries: Kingdom of Saudi Arabia, State of Kuwait, and Government of Bahrain. And it started by producing liquid ammonia and liquid methanol only. Eventually, and in 1998, the urea plant was introduced. So the first urea ship was loaded, and the Bahraini pearls were reborn again. But this time in a new form. Not a natural pearl, but as you can see, this is the Bahraini pearls now. It's in a form of granulated urea. And GPIC, since then, it's trying to build its organization to excel and become a key player in the industry by building its legacy on various of values towards achieving the ultimate mission and vision of the stakeholders. So I hope you enjoyed the historical journey. I hope it was different from what we've seen today morning. So we'll have a quick overview about the products handling and export section. Of course, you can see this is the manpower distribution and the export section. And I'll not go in a lot of details, but I can say proudly that 85% of our manpower in the export section are Bahrainis, which is a remarkable achievement. This is an overview for our section. You can see here, we'll start with the top left corner, the urea granulation unit. The main operations in the handling and export are three main operations. The first one is receiving and storing the urea through 4 conveyor belts. You can see it in the red arrows. And these conveyor belts stretch around more than a kilometer in total length to a storage of 100,000 metric ton. Then the second operation is the loading and export section, which starts with the scraper reclaimer at the storage at a design capacity of 1,000 metric ton per hour. And we have 7 export conveyor belts stretching 3.6 kilometers along the sea, reaching our jetty and the ships which to be loaded. You can see on the right side, this is an internal view for the urea storage area, and you can see comparing the ordinary humans, if they stand, it's like 13.6 meters height of urea piles that we are maintaining. The third operation, I'll just return back to this slide, is comparatively smaller operation. It's the 50 kilogram urea bags. We have this operation, but it's very minimum. It's part of a GPIC responsible care commitment to the community and local farmers. So, this is another aerial view for our system. You can see on the left corner again, this is the bulk storage, urea storage area. It stretches, its length is 500 meters. Maybe in this photo looks tiny one. Then you have 7 conveyor belts stretching on 3.6 kilometers, as I mentioned, reaching the ship loader. The total traveling time for product is 35 minutes. It's 35 minutes from the time product comes on the belt at the storage, reaching the jetty, which is already one challenge that I'll come later and speak about. We can receive ships of total length of 260 meters and 59,000 metric ton dead weight. This is part of some of the figures. As you know, urea fertilizer is exported to a lot of agriculture countries. So if we refer to last year, our export was scattered, majority to India and Australia, then USA and Brazil, and you can see the rest like Thailand, Turkey, and Africa as well. Yes, please.
Before we leave the one form, you have many terminals. You have 7 belt conveyors.
Yes.
Why you don't use one? You changing because of the change of the direction, or what? Because I see terminal 7, terminal 8, terminal 9. They have. Is that because of the changing of direction, or why not straightforward?
I will refer back to this photo. See, at that time, if we speak 20 or 22 years back, when the plant was constructed, the best construction was for conveyor belts. If it's 3.6 kilometers or more than 3 kilometers, it's preferred to be in ports. But nowadays, of course, the technology advanced too much in this field, and nowadays you can put single conveyor, as you mentioned, and technology. Now you can supply something called a pipe conveyor, which it will overcome another problem, because as you know, if using urea, it's exposed on the conveyor belt. But the new technology, the pipe conveyor, encloses the product and covers it from the time it comes on the belt until reaching to the ship. And this, we've seen it in different countries already. New plants, they are implementing this one. And by the way, pipe conveyor, you can transfer material in both directions as well, as you mentioned. And this is another, like, maybe a weird graph a little bit. This is about total urea ships loaded from GPIC. Before I come to Oman, I was there and we loaded 417 ships already, and the 418th ship is already under loading right now. This is since commissioning. These are a couple of photos for the 50 kilogram urea bags. This operation, as I mentioned, we have 2 lines of 120 metric ton per hour capacity, and a storage capacity of 5,000 metric ton. So, the core of this presentation, the challenges and best practices. As an export section, there are different challenges that you will be faced during the loading operation. And I can categorize them in 4 groups. We have the equipment reliability and the manpower readiness. We have the environmental and quality systems and legislations, locally and internationally, compliance to these regulations, and the direct customer's responsibility. So in each point of this, I'll pass by few challenges and how we could overcome those challenges. The first point is the environmental and quality system compliance. I know it's a long list, but in GPIC as a whole, we are complying to more than 12, 13 quality standards, ISO, OSHA's, responsible care. Of course, these apply generally to whole GPIC. What is the benefit of complying to all these quality standards? It ensures your system runs nearly perfect. Of course, nothing is there perfect 100%. This is why all the time you have the continuous review for the system to try to be perfect. So when you comply to all these systems, you'll have internal auditing, external auditing along the year. So your system is continuously being reviewed and improving. Another thing is the Sustainable Development Goals. SDGs. GPIC signed with the United Nations back in 2012, and we are committed and we are submitting our report fulfilling all these goals globally, and including, of course, AFA objectives also include these two. This is unique to our export section. As a challenge for urea producer, you need to be exposed or capturing the majority of the market. How you can do this? Because there are special markets, like Australian market. You need to have certain certification so Australian buyers can come to you and approach you. So you need to comply with the Australian Government Department of Agriculture certification. And this is a very challenging certification. The audit takes like 2-3 days. They go through a lot of documentation and field visits. They'll pinpoint every single corner of the export section because, you know, Australia is a continent and they don't want any organic matter to enter the Australian continent. So it's very strict and we are complying. So we are capturing good margin of the market. Equipment reliability, the second part. One of the main challenges that you face as an producer of fertilizer, you need to export the maximum quantity possible of your production to make out the maximum return possible. But at the same time, you need to ensure your system reliability and durability. As you know, you can run your system at 110% for 1 month, then go for shutdown for maybe another 40 days. But this cannot happen. You need to find the balance between exporting and hitting the best figures possible whilst you're having your equipment in ship. So from our experience, we noticed that in an export section, due to tight ship loading schedule, you know, all the time ships coming, and once ships are alongside, you need to load instantly. So we face the problem of some maintenance jobs, whether preventive maintenance or corrective maintenance jobs, they get delayed or sometimes partially done due to unavailability of the equipment or ship arrival. So what happens that if you have like 20 days of ship loading calendar days during the month, you'll end up by only having 7 days of maintenance period, which is very difficult to carry out on 3.6 kilometer conveyor belt system. So as an effort, we felt we need to compile the jobs. So we tried to tackle this issue by compiling these tabulated forms. Of course, we have a solid maintenance planning section, which they are supporting us on weekly basis by providing the weekly preventive maintenance and corrective maintenance jobs, even though we need to give the support as well to our planning and maintenance as well. So we do tabulate all the maintenance jobs, and we categorize based on the status, whether started, partially done, pending, not done, and based on criticality as well. So once the ship loading finishes today, we share that list with the planning team and the maintenance team, so instantly everybody knows what job to be tackled first, what job to be done next. So that was one of the solutions that we had to create, that balance between the maximum productivity and maximum maintenance. Another solution for one of the problems was belt condition deterioration due to the harsh environment. We observed that like production belts get deteriorated, the hardness increases, or it will become brittle, cracks will start developing, leading to downtime of the production and the export. So in line with the philosophy of the turnaround 10 years rolling, we are replacing now all the production belts, like each 5 years, 4 to 5 years, we are replacing the belts. And we started replacing the export belts, and as of now, we replaced 2.8 kilometer of the export system, and still we have 1 kilometer to go. Another issue, can you say what you can see in the photo? Belt, yes. This is a conveyor belt, a wet conveyor belt. Of course, prior to start loading operations, if you have like high humidity weather, the belt will look like this and slippery, and you cannot reclaim the material, the bright white free-flowing pearls, you cannot put them on this belt. Okay, so what will happen, you need to start the belts and to get them dried. But the issue, when the belt is wet, it will start going off center. So because we have one very nice program in GPIC, which is the suggestion program, one of our operators and employees came up with this idea. On the left side, you see this frame, and on the right side, you see this frame. I made it a bigger photos here. He suggested a temporary solution until we solve it permanently. We provided these deflecting rollers. Deflecting rollers. Yeah, side rollers. So imagine if the belt goes off center, what will happen? It will start rubbing with the steel structure. And if it started rubbing with the steel structure, it will start shredding. And this is the last thing you want to see, because your production will go down, your export will go down maybe for 4 or 5 days. So providing these deflecting rollers prevents the belt from rubbing with the structure, and that was excellent solution temporarily. Of course, still the trips were there, because we have another system for misalignment trip. But eventually we solved this issue permanently by installing these self-aligning rollers. You can see these are frames that designed in a unique way to auto-correct the belt movement, whether it goes off-center, right and left. So that part, this is a pin in the middle, and that frame will be turning freely right and left. So whenever the belt goes off-center, it will push it to the other direction. And since we installed this system, touch wood, we never had any downtime due to misalignment issue. Recommended, if still you don't have it. But by the way, the new systems, the new conveyor belt systems, they all comes already with it. This is another solution back to the issue of belt wetness. When the belts are wet and you need to start loading, you cannot, because you need to get it dried out. So from our experience, getting the belts dry take like 5 hours, 4 hours, 5 hours until it's fully dry. So we installed these parts on the conveyor belts. These are like a blade of a rubber compound, a special rubber compound. It works as a wiper, and once you start the belt, it will start wiping the whole moisture from the belt. And since we installed these, belt drying will take something around maximum 45 minutes. So what we gained in each restart of the loading, we gained around 4 hours instead of waiting until fully dry. This is another solution that recently we introduced. We install on each belt one of them. Yes, yes, yes. So that is another solution that we introduced earlier, past 2 years maybe. These are, the issue was in the right photo here. Of course, each conveyor belt construction, you'll have carrying rollers along the belt, like this. These are frames with the rollers on them. Usually it comes metallic rollers. This is what I'm coming now. This is the challenge. So the challenge was the life of these rollers is short, because when you need like something around more than 5,000, 6,000 rollers, you cannot like make stainless steel rollers and place them along the belt. So these are ordinary steel, carbon steel, yeah, uncoated. But the issue now here that they get frequently fail. They get corroded due to harsh ambient condition at the sea. Plus, the bearings will start failing, but the biggest problem is, since these are metallic ones, it will start damaging the belt, which is the worst even. So we came out with a solution as well. We installed the PVC and the HDPE rollers. These rollers has more lifespan. It's more gentle on the belt. Its unique design of bearings and all this gives it much more durability. And another benefit that we, to be honest, we never thought about was, after installing, it reduced two things. We benefit from two extra things. One thing was the noise level from a running belt reduced drastically from a running steel roller to this type PVC ones. So we reduced the noise level. The second was the power consumption by the motors that are driving the belt reduced also significantly. Yeah, so that was something, the current that is being withdrawn by the motors. So that was something that we did not thought at beginning, but that was like the cherry on the cake. Of course. Yeah. Possible because of the unique design of the bearing system and the whole thing, you know, when it's running very smooth. So, next point in the challenges regarding the manpower readiness. Of course, as you know, having a fabulous business cannot success without the people. Plus, even if you have highly skilled people and educated, but if they are not ready and in the correct mindset to carry out their responsibilities, again, you will not succeed. So you need to ensure, especially in the export section, because it's different little bit from the process plant. And the process plant, usually the operation, everything, once the plant is running smooth, everything in the pipeline, in the vessel, and the tanks. But here, you need manual operation of ship loader. You need a person who sits in the ship loader for continuous 2 hours, 2.5 hours, fully concentration to distribute the product inside the ship without hitting the ship structure, without having any failure, especially like in these impacts. So you need the people to be fully ready when they come to the shift. So we have different programs that in lines with this objective. And of course, this only comes when you make people feel the ownership of the place that they are working at. So if you could achieve this, you can excel. So we have different programs set in place. We have shift talks, safety talks, we have emergency mock drills, and we have the suggestion program, in addition to other programs as well. So what is a shift talk, a safety talk? A shift talk, safety talk is a group discussion that a loading supervisor carries with his shift team. And in this talk, they will discuss important issues, important topics regarding the operations, regarding related incidents, regarding past incidents. So you make your people fully aware about what you are going to do. And the title itself, it's shift talk. It's not shift message. Because if you said shift message, it will be a one-way communication. I send you my message, that's it. But here, we are naming it shift talk. A talk, what does a talk mean? That means there is a conversation. That means we sit around each other, we discuss, we talk about the shift things. So it is a talkative session, makes everybody involved, and make them aware of everything going around in the organization, operational-wise, administrative-wise, safety, reliability, and everything else. Usually, we take one shift talk per shift, so each employee will at least attend 12 shift talks along the year. So it's like monthly ones. Another important practice that it is recommended to have, and I'm sure a lot of organizations, they have it, it's the emergency scenario mock drills. These are simulation of emergency actions that you need to take. So we have a database for potential incidents or any related scenarios that make your people ready for these things once happen. So the full team will be engaged physically in these mock drills. So we plan it in the shift and we distribute the roles and we try to come up with different solutions later on how we can tackle this emergency issue. For example, we have like, this is like a snap of the list of scenarios that we have. For example, we have like one of export conveyor strips during urea ship loading, like you have urea spillage, you have urea ship drifts away from jetty during loading. So all these scenarios, we practice them practically to be ready if it happens. Another beautiful program that we have is the suggestion program, and really I love this program because it empowers the employee. It makes them sense that ownership feeling that you want in a person. Because if you know that you're going to the work and leaving after 8 hours, that's it. Okay, you're doing your job and getting paid for it. But if you feel the ownership that you're contributing in something really and physically, here this will be something else higher than ordinary job that you do. So you can see on the right side, these are different photos of a lot of our people's suggestions that they came out with. And we resolved a lot of issues and we tackled a lot of problems through this program. And so far, from this program start up to now, we have more than 330 suggestions from different peoples, from different ranks in the work, all these ideas being implemented. Direct customer responsibility. One of the challenges for me as a loading supervisor is the communication establishment. Whom are the direct customer for me? It's the first one is the ship crew, ship captain, ship chief officer, because I'll be dealing directly with them and loading their ship. The second are the agent representatives, and the third one are the port authorities. So these are sample forms that we developed past years. These exchange information forms help in identifying a lot of loading aspects operation before ship arrival. So we will not waste time now on agreeing on different operational points when the ship is alongside. With this information, this will be sent to the ship 1 week, 10 days before its arrival to Bahrain. So we'll have all details of the loading aspects and we'll be ready for it. So once the ship is alongside, we go on board, sign these documents. Some ship crew, especially the captains, usually they complain. They say, this is too many paperwork for me. I have to sign a lot of papers. But we do believe spending half an hour or 1 hour before start of loading between myself and the captain and agreeing on all aspects of loading, operational, safety, security, an emergency, fire on board ship, all this we agree on it in 45 minutes, and then I will not see you until we finish loading because we already pre-agreed on every aspect of the loading. So by introducing these forms, we are ensuring a very safe and smooth and efficient loading operation without having any surprises during the operation itself. This is another publication that we came out with. Of course, it's part of our responsibility and responsible care commitment because we believe as a producer of urea or any product, you not need just to take the responsibility of product from your storage to the ship. No, you should go beyond because the ship is not the end user for your product. So as part of the responsible care, I ensure even the ship crew, by giving them this guideline for handling granular urea, I ensure they are aware about my product specification, quality, how to handle it, its safety, how to transfer. All these points are mentioned in this booklet and we explain it to the ship crew as part of our responsibility. This is another form that we introduced to improve our system, our loading operation. This is a customer feedback form. After completion of any urea ship loading activity, we submit this form to the ship captain and chief officer, and they will evaluate our job. And we take all the observations and all the comments in it seriously, and we resolved a lot of issues. And you can see in this curve, since we started implementing this system, we started scoring like 4.1 over 5. The red one is for urea ships. And along, of course, this figure is an average for the whole year. So we could improve slightly, and during this year, we could improve significantly the services and how we do act with the ships, with the ship crew, and how we do our job. As an outcome from this, as an outcome from the customer feedback, we received a lot of complaints from ships on delays from the port authority side, which is something beyond our control. But even though we did not lift the issue open, after communication with the port authorities, we came out with this exchange of information with the port authorities. So we mention all ships. These are monthly reports sent to the ship authorities. We mention all ships that are calling GPIC during the month and all other details from like arrival time, anchorage, anchor away, delay in berthing, and delay in unberthing. And since then, the time delay of our ships, whom are calling our jetty, reduced significantly, and we are tackling it positively with the port authorities. So, to wrap up, the conclusion, to have a synchronized system and homogeneous system and a successful system, you need to have a synchronization between all these aspects, all the aspects that I talked in this presentation. So you have to have the equipment reliability, which is maximum maintenance possible versus the maximum export, and environment compliance, direct customer responsibility, and of course your manpower readiness. And if you could create that balance and synchronization, you'll end up by achieving a lot of targets, sometimes exceeds what you expect. Like, for example, we could load maximum quantity for a single ship of 50,356. That was in 2012. And then in 2016, that was the second highest, 50,000. And various other achievements that will lead to a better and brighter future for your business. By this, I'm done. And I hope you enjoyed this presentation, because I enjoyed it a lot. So thank you very much. How many? Palletizer. For the bagging system, we have 2 bagging lines, as I mentioned. So the full bagging system is fully automated, pneumatic with the vacuum nipples, and ends with the palletizer. We have 2 palletizer. The manufacturer is, it was Nova, the palletizer. So I can give you the details later. I'll get you the full details if you need about this. The same, but we are now working on improving the system, because it's being run on very low scale, only for the internal market in Bahrain as a support. So we are trying to come out with more ideas, because maintaining the system is becoming another challenge. So maybe in my next presentation next year, I will mention the bagging line challenges, maintenance, and the palletizer as well. For? No, we don't have loading of urea bags. No ship loading for urea bags. The bags only for local markets, sent by trucks only. It's a very small market, and you cannot compare it with the export. Problem of humidity, as I showed that photo of the wet belt, it is a problem, as you know, because you need to suspend loading when humidity is 75% or more. For us, we put the margin as 75%. So, because once 75% exceeds, the system will get wet and urea starts absorbing the moisture from the ambient air, which you don't want to happen, because you'll end up by caking problem. And if urea started caking, it will be very, very bigger problem for everybody. So this is why we stop the loading before even humidity hits the 75%. So we are keeping close watch on the 3.6 kilometer length of belts to ensure they are not wet, they are dry. And we are already studying providing sort of a air blower system to keep the belts dry. And this system is still, it's only a concept. We still did not apply it, but it comes with a heater as well. So keeping the belt dry, it will not be an issue if you implement this system. Yeah. Which one? Yeah, pipe conveyor. Yeah, pipe conveyor is a new technology. It's a new technology now available. I've seen different manufacturers. They produce, it will be like 2 pipes on each other. Now, a conveyor belt, you'll find the carrying side and the return side. And you have a frame of 3 rollers under the belt. Imagine if you have 6 rollers, 3 at the bottom and 3 on the top, and that belt is folded on itself. Like it's the ordinary belt, but the frame design makes the belt fold on itself like that. The conveyor is the conventional conveyor. It's nothing special about it. It's only the arrangement of rollers. The frames will let the belt enclose on itself, carry the product inside, and transfer it. Okay, yeah. Yeah, neither us. Yeah, neither us. But it came. Yes. It's difficult. It's difficult because of the sensitivity of urea. Because at the end, yeah, you're most welcome there. Thank you. Thank you.
بسم الله الرحمن الرحيم. في شيء شغال في صوت؟ اوكي. السلام عليكم ورحمة الله. My name is Uthman from Arab Potash Company, Jordan. In this presentation, I will would like to share you with our challenge, to keep our plants in high availability and reliable. Before that, I'd like to start a brief history about our company. Arab Potash Company, founded in 1958 by Jordanian government and other Arabian countries, Iraq, Libya, and Kuwait, and other private sectors. ABC gave the concession for 100 years to exploit the Dead Sea mineral, not only the potash product. But due to the political situation at that time, the actual production or the commercial production started just in 1983. The plant, located at the south end of the Dead Sea, it's about 110 kilometers from Amman to the south side. Now we have the total production of 2.45 million ton per year of different potash size, fine and standard, and granular products. General overview for our company. ABC consider the 8th largest potash producer around the world and the sole producer in the Arab world. It's also considered one of the best company among Jordanian corporations for many issues like safety records and governance sustainable. In addition, also the Arab Potash company, in addition to the core business of producing potassium chloride, it invested in several downstream and community industries related to the Dead Sea salts and minerals like bromine, KNO3, and other directives. Arab Potash Company contribute on the Jordanian economy, as its employee more than 2,000 workers around the whole locations, in addition to many local outside contractors whom depends on the Arab potash activity. ABC mission. In general, ABC have one mission to participate and lead the fertilization industry in Jordan through the mineral resources of the Dead Sea and integrated the fertilizer industry in Jordan and develop the downstream industries such as bromine, magnesium oxide, potassium nitrate, and calcium phosphate, and other. And develop the Jordan export and contribute to the cross-national products. We have 3 plants. The categorization depends on the process used to produce the KCl. The old one, which is called the hot leach plant of 1.4 million ton capacity, was established in 1982, and the cold crystallization plant number 1 of 0.6 million ton per year, built in 1994, and the last one, CCP2 or cold crystallization plant number 2 of 0.5 million ton per year. It's built in 2009. So we now around 2.5 million ton per year. Availability and reliability. Now we are facing these challenges to achieve our targets to keep the plants, the 3 plants, and the utilities in high available and the equipment reliable in a good manner. The first thing is the nature of the salty media we are dealing with. We are using the Dead Sea water of high concentration with salt of different mineral. This will lead to high corrosive of the piping system, tanks, even the equipment itself, the pumps and other issues. Also, the process itself, because it depends on many variables, which is not easy to control all of these variables on a time. Also, we are working on the hot weather, which reach about 50 degrees on summer. Another problem regarding the salt accumulation on the equipment and in the equipment. The last one is the spares availability. As you know, we are far away from the manufacturers, so if you have a shortage in any spare, you need at least maybe 3 to 4 months to get this spare, if it's on shelf on the manufacturer. So unless you have improved your defense with good maintenance planning and your own maintenance philosophy, you cannot achieve your target to keep your plants running without any interruption. We are using the most common factors that used to calculate the reliability factors and availability: mean time between failure rate, and mean time to repair, reliability factor. This depends on the source data. For us is the DCS data, and for the most critical equipment, we have developed a tracking sheet, downtime tracking sheet for this asset. Okay. How to increase the reliability? Of course, each failure happened let's say abnormal failure has its own analysis and study and the corrective action made accordingly. But these are the main issues that the company focused on it. The first part is the training of the employee in both parties, the operation people and the maintenance staff on all levels. So because the operator are the who is the responsible to operate the machine as it's designed for. So he has to train to how to operate this machine as it's designed for and avail the design performance parameter for it. At the same time, highlight any deviation or any abnormal condition regarding to this machine. Maintenance staffs at all level should be trained or already trained to implement the best practice for implementing the maintenance activity for the jobs. The second thing is the lowest cost is not our first choice. So we are focused on using high quality materials, regardless whether if it's a new equipment or lubricant, spare, or any thing. Of course, you will pay more at the beginning, but it will give you more benefits regarding the working time. The third one is to invest in the redundancy or equipment redundancy. Many machines have, as we are working in harsh environment, so we are invested to put a redundancy to avoid any interruption for the production. At the same time, give the maintenance crew the enough time to perform the maintenance activity as it's recommended by the manufacturer or based on our experience. BM schedules. BM schedules within our ERP system, all equipment have its own schedule. This includes not only the checks, also the condition monitoring and inspection. So we have a periodic measurement for vibration, temperature, beside the online measurements for the critical equipment. As the human being is the source or the source of any problem, we are trying to avoid the interruption of the human being by using the automation solution, whether for the control or the process control or for the data gathering. Critical equipment. Each plant, we have 3 plants, so in each plant we define 10 critical equipment that our calculation for reliability factor and availability calculation based on these and the below factors. The first one, the single line equipment. We have many equipment which is a single line without any redundancy, such as dryer in all plant, or any equipment that affect the safety and environmental standard. Also affect the product quality level. These are the 10 critical assets in the whole plant. We see most of them are the single line, but that doesn't mean that we don't tracking the other assets. Each asset tracked separately, but these are defined just for our calculation for the availability and reliability factors. These are the reliability factors for the critical equipment at the old plant, at hot leach plant. Starting from Jan to up to September of this year, we noticed we achieved high reliability factor, starting from 99 up to 80 for some equipment, and others are 89. So that's within our targets and within our limit. Maintenance planning department. As one of my colleagues who presented that, maintenance planning play a big role in the equipment reliability and enhancing the reliability. ABC planning department has 3 sections: BM and reliability section. They conduct a periodic vibration measurement of all rotating equipment, continuous equipment condition monitoring, in addition to oil sampling and analysis. Also to conduct root cause analysis with other related parties, operation maintenance, field maintenance people, for any failed happen. Planning and scheduling, the role to schedule the BM activity for all assets in weekly basis, schedule and manage plants turnarounds and shutdown, also and issue weekly maintenance plan for all the section. Manage and schedule backlog of work request and work order, avail required resources, spares, tools, etc., and manage the outside services. The third section is the inspection. Inspection section, it's almost the same of BM, but for the static equipment, for piping and tank or fixed equipment inspection. So they have their own schedule to conduct a periodic inspection for the pipes and issue the reports with the recommendation. This is the root cause analysis, sample of root cause analysis that carried out during 2018. Mainly it's focused for the unexpected failure, such as shaft broken, shaft failure, or bend, or any blockage happened. All of the corrective action and recommendation raised from this analysis were implemented. This is a sample for one root cause analysis for the broken shaft of one pump at CCP plant with recommendations. So they describe the problem and what's the finding, the main cause of the finding and the recommendation. Crystallizer unit at all the plant consider one of the main important unit at the hot leach plant for both quality and the quantity of the product. So any deviation or failure on this unit will affect both the quality and the quantity of the production. Based on process and quality requirement, there were a modification happened to improve the crystal size of the production. So this modification were by adding a notch. Sorry. Okay, adding a notch near the agitator blade and increase the height, insertion height of the blade to be more in the inside the crystallizer. This modification carried out in communication with the manufacturer or process consultant. It's okay, gave the good result, but an unexpected problem happened for the reliability of the crystallizers. So the modification done, but the size of the bearing cartridge shaft were not considered in this design, so we got a bad results for the reliability of the crystallizers. The modification required the units having longer bearing cartridge shaft length, so the length increased increased by 26 inch, which is 40 percentage, without any consideration to the size or the diameter of the shaft or to the material of construction, which caused repetitive shaft bend and backing failure with more downtime. For example, after the modification, the worst case for this resulted from this modification is a crystallizer number 3. So we tracked the shaft bend problem starting from immediately after the modification up to June 18. We found it's more 6 failure and affect the products and also the quality of the product due to unexpected design. Okay. So many analyses in coordination with the manufacturer, and approximately we reached to the final recommendation and solution to avoid such interruption and low reliability of the crystallizer. The first one install limit ring. Okay, this will keep the shaft or the agitator within element without whipping, and modify the shaft, the bearing shaft, the bearing cartridge material shaft to Inconel instead of the Uranus B6 material, which have more hardness material. Also to use spring-loaded backing gland. This will make a self adjusting of the backing instead of stoppage the crystallizer, and make the adjustment of the backing, and avoid, by this solution we avoid many interruption, many breakdown. Also to investigate the better liquid level control by using measurement and instrumentation devices. These are the sample of our plant's availability during this year. It's shown that we are achieved good results regarding this year, except April. We have a problem on the dryer ID fan due to the shortage of spare parts. It was the motor, so the availability of the plant reduced to only 75% instead of our target 95%. For the CCP1 plant, it's good, so the average availability is around 97.3%, and it's constant among the whole month. CCP2 has the same thing, and we achieved a good record of availability. Our targets actually for the plants is 95. So our achievements are above in all plants. This is for the harvesters. This is the machine that harvests the raw material from the Dead Sea. Also, it has a high availability during this year, reached to 96. This is a sample of the reliability factor calculation for some assets in hot leach plant. In monthly basis, this report issue, and we are focusing on the red color equipment, and make the analysis and make the required corrective action to increase or eliminate the break-in for this equipment. This is the mean time between to repair. It's okay, except we have the last two equipment, centrifuge number 26 and product centrifuge 45. It takes a lot of time. Also, the deep identification done and implement the corrective action. KPI reliability factor. Also, it's okay for most of the equipment at hot plant, except the crystallizer number 4, as we said before. Our future plan to enhance and increase the reliability of our plants and equipment for the crystallizers. Now, the crystallizer number 2 is the replacement of the crystallizer in progress, and the lining of crystallizer number 3 and 4 will be replaced next year. Crystallizer number 5, the drafted tube, will be modified along with the drive system and rubber lining. For the pumps, we have a project to rehabilitation projects for 18 pumps. The main pumps, including concrete, metal base, and suction and discharge pipes. Replace frequent fail pump due to bad selection, as it's maybe happened among the plants. Sometimes you purchase the wrong selected equipment, so we plan to replace them. For the thickeners, the top covers of the hot thickener will be modified and will be replaced, and modify the rake lifting mechanism to be hydraulic instead of the mechanical mechanism. Modify also driving and lifting mechanism for the other thickeners, second and first stage thickener, and also a new, we call it mother liquor tank or thickener, will be built next year. Or the project will start next year, and hope we finish by 2020. For the centrifuge, purchased a 6 new modified centrifuge for both sides at Carnelite and the Progress. It's the location where this centrifuge found. Modify lubricant system of the old centrifuge, and modify the pillow block and feed pipe for more stability. Also, we have a trial to use a new centrifuge from a new supplier, which is called IMM, just to compare the reliability of this machine and the performance. All of these modifications done upon our notes and upon our finding. For the build filter, also the complete rebuilds will be done for both filters, 11 and 12. We have also the screens. As we said, we are investing in the redundancy, so a new upgrading screen will be added at hot leach plant to enhance the reliability. Conveyor belts, modify belt number 40 to match the increase in production rate to avoid the overloading of this belt and unexpected breakdown and failure. Upon our inspection reports and findings, both the main dryer of CCB1 and CCB2 will be replaced, and the purchasing process now in progress with the vendors. For the boilers, now we are almost reached the end of lifetime of one of our boiler, and the pressure part will be replaced within 2 years. That's all, and thank you.
السلام عليكم ورحمة الله. راح نقدم برزنتيشن عن السولت مونيتورنج بروجكت اللي هو عن نظام سيطرة وفي تحكم في نظام الملاحات الشمسية. البرزنتيشن تم تحضيرها بمساعدة زميلنا المهندس معاذ الرجدان. The presentation content will highlight on the resource of the potash in our potash company, and the process and capacities for our system. Also, we will have a look for the solar pond control strategy. In addition, for the main operation obstacles in the solar pond system, then we will move to our case study salt monitoring project, including the project scope, the battery limit, also the methodology of work and the main finding, and the gain benefits from this project, including scheduling the dredging plan. Okay. All of us knows that the potash in the Arab country is coming from the Dead Sea, and you can see this photo from Google. The Dead Sea is located in the west part of Jordan, east part of Palestine, and it's located in the highway between Amman and Aqaba. The Dead Sea is the most hypersaline lake in the world. Its salinity is around 340 grams per liter. It's contain about 14.5 magnesium chloride, 7.5 sodium chloride, 3.8 calcium chloride, and 1.2, only 1.2 potassium chloride. And Dead Sea is considered the richest source for magnesium bromide in the world. It's contain about 0.5%. Sorry. Thank you. Okay. And all of us knows that the Dead Sea is the lowest point on the earth. It's level now around minus 433.1. You can see Amman here in the mountain. You can see the Dead Sea level, and you can see the Mediterranean Sea here. Okay. These are the most salt extracted from the Dead Sea. We have potash, we have table salt, industrial salt, also BK, potassium nitrate, and bromide and its component, chloride and its component, magnesium and magnesium alloys, sodium hydroxide. And the total dissolved solid in the Dead Sea, it's around 43 billion tons with 2 billion tons of potassium chloride. Okay. We are occupying about 262, our company occupying this area, because we need around 111 square kilometer for our solar pond system to precipitate our raw material kernelite. Our process starts from pumping the Dead Sea brine through main intake station from the Dead Sea. We have 4 intake pump stations through those 2 pipes with a diameter 2 meters. The brine is being concentrated and saturated with sodium chloride. Then the sodium chloride is being precipitated and dredged through a special dredger. Then we achieve the saturation point with KCl in order to precipitate our raw material kernelite in this area. After that, the raw kernelite is being dredged by a special harvester called harvester machine supplied by F.L. Smith Raco, USA. And the slurry is being sent to 3 plants, as mentioned by my colleagues, the hot leach plant, and the coated crystallization plant number 1, the coated crystallization plant number 3. This is a schematic diagram describe our process from the intake station to the salt pond. The brine flow pattern is in zigzag flow just to gain more retention time in our ponds. So this is the salt pond up to here with a total area 69 square kilometer. Then we have a small pre-kernelite pond to control the saturation point. We have the kernelite pond. We have 2 systems. We call this the old system. This is the new system. And we have recovery pond. This is we try to achieve 0 liquid discharge by sending back our brine from the plants to the solar pond system. And in order to produce 1 molecule of potash, we need about 12 months to precipitate our kernelite. The capacity of our ponds now, we are able just only to produce 12 to 13 million tons of raw kernelite, and this is sufficient to produce around 2.45 million tons per year. This is a photo for the harvester. This is for a dredger to remove the salts, and this is for our intake pump stations. This is again a diagram to show you how the system is worked. Now, the big challenge is the design and modification consideration. We have big challenge in the area that we have to avail good land with a topography, with soil condition. We have to avoid seepage. We have to avoid cavities. We have to avoid sinkholes in the area. The second issue is the climate. As you see, we are mainly depend on the weather condition because our system is working in evaporation. As we have sunshine, it's good for us. Rain is bad. Humidity is bad for us. Wind direction is helping us in mixing the solution. The next issue is the transportation. We have the suspectability of the area for the flooding. As you know, this year, Jordan faced 2 flash floods on April and on November, and this has hurt us a little bit. And we have also the freshwater interest to the system and operating manpower. The main control parameters we have to control, we have to achieve the kernelite point. This is the key parameters in our control. Also, we have to avail the required ratio between the halite and kernelite bonds, and this is an important issue for us for controlling our system. And we have to avoid achieving the upper limit Bashifite point. Bashifite is MgCl2 to H2O. The last issue, we have to control the bond depth just only if we approach the upper limit, and this is very important for our fleet of harvesters and our fleet of dredgers. As we mentioned that we have to control the kernelite bond in the middle of the system, so in order to avoid the precipitate sodium chloride, that will hurt our plants and will reduce our capacity and will hurt our quality, so we have to control our system, and this is being done by achieving the kernelite point. So we have day by day with site measurement, we have to look for the concentration gradient in the area, and you can see here in 26 how the last flash flood hurt us. The density drop was here, so we were forced to stop the intake feed station from the Dead Sea. Another control parameter in the kernelite bonds, here we are looking only for the level of the kernelite bonds because the concentration gradients is not jumping a lot in these bonds. So we have just looked to avail the good level for the harvester machine, and we have to avoid discharge a lot of K-ion out of the system, and we have also to avoid achieve the Bashifite point. We are carrying out 2 different mass balance, one for salt bonds and one kernelite bonds, and this is being done by a rigid mathematical model, and this mathematical model is used also to evaluate any new process and any operation obstacles. In addition, for the monthly mass balance to calculate our production rate, we are using our own data sheet. The main operation obstacles for our system, we have the salt accumulation and reef formation in our system, and this has hurt us in terms of blockage of the system and cause an uneven distribution for our brine and losing the concentration profile in our system. The second issue is the sinkholes and cavities appearance in the area as a result of a dropping of the Dead Sea level. The third point, which is part of it, due to sinkholes, is the seepage and leakage, and you can see some of the leakage and seepage to the truss channel, and this brine is being loosed and back to the Dead Sea after pumping. And the last thing is how to deal with the freshwater interest to our system, which cause mainly dilution for our brine, and in some instance it's accelerate formation of the reefs and salt mushroom in our system. So in order just to have a look and to be very close to our system, we are carrying every 2 years a project called Salt Monitoring Project. The Salt Monitoring Project is aimed to capture an aerial photo for all ABC concession area. Also, this will be, of course, the area photo corrected geographically and geometrically. Also, we have to assess the operation status of our solar bond system. Also, we have to make a survey for any suspected sinkholes and cavities in the area, and we have to surveying the salt ponds surrounding area, including the truss channel. This is the battery limit for the project. This is our solar pond system. We have also to survey the part of the Dead Sea. We are also the truss channel. We mean by the truss channel, the channel separate Jordan and Palestine and Brine, and the water coming from Wadis is back through this channel to the Dead Sea. And also we have to suspect and inspect the surrounding area to our plans, because this area will be our future for expanding our solar pond system. This is the main tools used for our system. We are using aircraft equipped with high-tech ultra cam camera, and we have also using a skiff with we have a check bar 5 meter depth, a brine density bar just to bring some samples from depth of 2 meter to check if there is a layering. Also we have thermometer and hydrometer. Also we have a navigation device, GPS system. The first step in our work, just we have to determine the flight lines. What will be the path of the aircraft? Okay, so we determine the flight lines. The second issue, we have to carry out field sampling. We have to sample from the surface. We have to sample from the depth and send the samples for the labs. We have also to determine the depth of the brine based on the area photograph, and you can see it's 2 color here. You can see this point is more depth than this point. So, and this is the tools used during our survey. The next step, we have to carry out a geotech network check for the area, and we have to correct this photo based on the salt accumulation, what we call in a gray scale. The next point, we have to analyze our observation in the site in terms of cavities, in terms of seepage, and we have to analyze and we have to put an action how to deal with this. And the last step, we have to determine the spreading percentage of the salt mushroom. This is very important because salt is being precipitated from the beginning to the end of the system. And as a rule of thumb, because the brine is more diluted at the beginning of the system, the precipitation here, thickness is around 25 centimeter. As it passes here, it reaches at the end of the system up to 5 centimeter. So at the beginning of the system, sometimes we have some blockage to the system, and you can see from the red color as you see here means that there is no depth for the system. This color means that we have enough depth. So we have to maintain at least 1 meter depth to ensure that our brine is flow even without any problem. The major findings from this project, the first point, we have to look for the evaporation area. As much we have evaporation area, we will produce more. We found during this year that we have some inactive area, we have some losing area from the beginning of the system. You look for this, we are losing this area, and we are losing some area in the cornelite ponds. And this represents about 8%, and we lose due to presence of this inactive area about 2%. So this is, at the end of the day, a production loss. The next finding, we have to check the concentration profile, as we mentioned, at 2 different layers. Because this is very important, so we have a look here, so to see if there is a brine restriction or brine layering or reverse flow, because if we have reverse flow, you will have an adequate control for your system. Also, you will lose, in some case, some control. As you see here, we have here some salt reef built up here. So we found that the brine is more concentrated here, and at some point it will reach the cornelite, and we will lose part of our product here. So we have to take a decision to open this salt reef. The next issue is the weir. Weirs is used at our system is to transfer brine from pond to pond. So we have to maintain them at maximum depth, about 80 centimeter, because if we make them deep, you will have reverse flow. Reverse flow means that you will lose high concentrated brine from this to this, and of course, again, we have a production loss. So we check all the weirs depth, and we found some of the weirs very deep, so we have to reconstruct them again. And some of the weirs we found them very shallow. This means that the brine will be restricted, and we have to deepen them again. The third challenge was freshwater interest to the system. Freshwater interest to the system means cause dilution to our system, lose concentration profile, in addition to increase the salt mushroom build up in our system. So in our area, because the Dead Sea is the lowest point, the rain coming as surface water to our area, or it will come escape from the aquifer through piping, and you can see here, it goes here, cause baby mushrooms, then it will be larger and larger, medium up to large, and it will then, at the end of the day, it will connect as salt reefs. And you can see from this photo, we found that some water is coming from beneath and make some holes, and we found this is diluted water, and cause a lot of problems for us to control our system. The fourth finding was the dredging activities. As you remember, we have a special dredger design to clean the salt and to reclaim the salt for our reclamation area. So we have to make our plan, because we have now only 3 dredgers, and we built 2 new dredgers, so we have to make a plan where to dredge. During the survey, we found some area blockage, so we have to move our dredgers to it. Also, we have to put some area are shallow again, and we found that the first point system has some restriction, and we are built now a new dredger. It's under commissioning. It will deal with this situation. The next issue is the salt reclamation area, and this is one of the major challenge for Arab Potash Company, because we are removing sodium chloride and build as a capital project separation dike with sodium chloride. But these dikes now at the upper limit I mean upper height, it's 25 meter. Exceeding this will hurt our system by 2 things. It will cause a static pressure on the area and increase the sinkholes and cavities in the area. Another issue, it will make the area like it will capture the wind in the area, and this will not help us in terms of evaporation. Sinkholes. We found during the survey we have some sinkholes in the area, so we have to send some loaders to deal with it and close it. We have some seepage. We found some water, some brine escape from here. We cannot find any brine leakage here. We go by using a drone. We found that the brine is escaped from this area. Also, we found a lot of sinkholes here. Another issue, we found a new sinkhole appears behind an old sinkhole also. Also, we use dye techniques to see where is the path of the brine goes, because sometimes you have the brine escape from here, you will find it in somewhere here. It's not direct come in this way. Last issue and the main finding, we have to follow the elevation of our dikes. We have from the old aerial photo, we have the elevation, so we compare it with the new elevation to see if there is settlement on the dikes, because we have operation level for our brine in our salt ponds, so we have to control it very much, otherwise we will lose from our inventory. Last thing, after all of this, we have to plan, we have to schedule our dredging plan, otherwise the system will be closed, plugged, so we have to open. This is our new dredger, Jarash. It will be at the beginning of the system. This is a mini small dredger. This is just in case of emergency to open any closed bath. So, as we mentioned that we are precipitate about 16 to 18 million tons per year of salt. We have to get rid of them. So we have to schedule to remove them. So we have 3 old dredgers with a capacity of 15,000 cubic meter per day. So we have to consider the running hours during the years, the days, and we have the most important to consider the brine elevation, which shall be controlled around this figure. And as a rule of thumb, to maintain our system working, we have to dredge every year 7 to 8 square kilometer, and we are considering all what mentioned, and this is what I mentioned before, what is the main criteria we are depending on to maintain our system and to build our schedule for dredging. At the end of the day, we build our schedule for 3 years. As you see, we have the bond name, we have the priority, we put even in the priority, and we divide each bond in sub-bonds, area A, B, C. So we put the priority for each area, and then we have to put the timing when it should goes in and when it should leave. Okay, so we built our schedule based what you saw in the presentation. I hope this was clear, and thank you everybody.
والإعلان الأخير هو الدعوة لغداء اليوم في مطعم طيبات وبالهنا والعافية للجميع.